Hello students. Okay, I am live. मेरी आवाज आ रही है, मैं दिख रही हूँ सभी को, मुझे बस चैट बॉक्स में बता दीजिए. हाय एवरीबॉडी जो भी वेट कर रहे हैं आज के सेशन का. तो आज हम ठीक है. गुड आफ्टरनून Alvin. Everybody, hi. Again, I know that I am a new face on this channel, but I've already taken one session which happened like 2 days back. So we discussed a little bit of chemistry in that session. We did some questions, but right now in this session, what we're going to do? In this session, we are going to complete the entire organic chemistry. Okay. So I'll be looking at the chats also. So here, if you are attending this session live, what will happen with you guys? You can ask me any doubts that you have in any mechanism that we are going to do in this session. So let me restart like what are we actually going to do in this session and how it is going to help you in your JEE exam, which is just round the corner, just one day more to go, right? So in this session, we will be following the back approach. The back approach is what? What we used to do, we used to study one mechanism and then do the reactions based on it. But right now, the approach that we're going to follow for this revision session, revision marathon for organic, is we are going to look at the kind of questions asked and then we're going to solve those questions, like what kind of approaches are actually asked in your JEE exams, right? So in that manner, a question will be left untouched, especially in your organic chemistry, right? Beta, if you see this video, if you're organic, see, this can be like, if you know basic things about organic, like what is inductive effect, what is a mesomeric effect, like if you are even aware about the definition of those effects, this session is going to be really helpful that you can solve approximately 99% of your organic paper. That is my guarantee. Because in this session, I have included everything from mechanisms like SN1, SN2, E1, E2, and what is the competition between them, and all the name reactions we are going to do in this session, and also all the approaches like the ring expansion approach, and what's the astatine order, what is the ortho effect in the carboxylic acid, in the aniline group, everything, every nook and crook is included, and what is the purpose of reagents like LiAlH4, and what is the difference between those reagents. LiAlH4 reduces what kind of substances, NaBH4 reduces what kind of substances, and we're going to even study about what your oxidizing agents, like which oxidizing agent oxidizes ketone to carboxylic acid or aldehydes to carboxylic acid. So we are going to do each and everything in this session, and we are starting right now. Okay? Now let us start. Before wasting any more time, let us start this session, and this is my humble request to you guys to go to the Vedantu page and actually download the JEE Main Rank and College Predictor 2024. What will happen with this? Like if you give your JEE exam and then when you come back home, you might know how much score, how much you're scoring, and you can put down that score in this JEE predictor, and then you will get to know like what can be your possibility of the rank in JEE Mains. So this is a very helpful tool which you can guys download and go and make use of it. Now let's move on to the very first topic of your organic chemistry without wasting any time. With the duration of this live is approximately 3 hours. In 3 hours, I am going to complete the entirety of your organic chemistry. Whatever is asked, whatever kind of questions are asked related to organic chemistry, we're going to do all of it, and you can ask me your doubts. Now, let's not waste any time. Hello, everybody. Hello. So the number first thing that you can see on your screen, this is very important. Why is this important? Because sometimes questions are asked like what is head-on overlapping, what is parallel overlapping. So quickly see the definition. Property, like how sigma bonds are formed. Sigma bonds is formed by axial or head-on overlapping, just like this. Correct? This is a sigma bond, and your pi bond, how is it formed? It is formed by parallel overlapping. For example, here like this, parallel overlapping will occur, and pi bond formed by parallel overlapping. Electron cloud in the sigma overlapping is along the internucleus axis. Can you see? It is along the internuclear axis, but in pi bond, how the electron cloud is there, bacha? Electron cloud is actually perpendicular. This is the internuclear axis, and therefore the electron cloud is perpendicular to the internuclear axis. Bond strength, sigma bond is stronger and pi bonds are your weaker bonds. This concept should be clear of each and everybody. Okay, now let's move on to the next question. Let me find the remote. It is here. Okay, now next question which is asked every time in your JEE exam is this basic question to find out the hybridization. So I'll tell you a very easy trick how to find the hybridization of each element. For example, if any hybridization of carbon is asked. So if any hybridization of carbon is asked, you will do nothing. You will just count the number of atoms attached to it. For example, in CH4, how many hydrogens are attached to CH4? 4. Therefore, its hybridization is sp3. Similarly, if the hybridization of C double bond CH2, this is asked. Now tell me how many atoms are attached to this carbon. How many atoms are attached to this single most carbon? So I can count, this is 1 atom, this is 2 atom, and this is 3 atom, right? So in this carbon, 3 atoms are attached. Therefore, the hybridization of this carbon will be sp2. Similarly, if with one carbon only 2 atoms are attached, the hybridization will be sp. This is how you calculate hybridization of carbon. Now let's move on to the hybridization of nitrogen. So with nitrogen, what you're going to do, how many atoms are attached? If 3 atoms are attached, hybridization is sp3. Okay, if 2 atoms are attached, it will be sp2. If 1 atom is attached, hybridization of nitrogen will be sp. Remember this thing. Now H2O. In H2O, we are finding the hybridization of oxygen. So in oxygen's hybridization, if with oxygen only 2 atoms are attached, look at here, hydrogen, only 2 atoms are attached to oxygen. This is how H2O structure is there, correct? So with the oxygen, only 2 hydrogen atoms are attached. It means its hybridization. Here oxygen's hybridization is sp3. Okay. Similarly, if only 1 atom is attached to oxygen, its hybridization will be sp2. Remember these things. Okay. So this is how you calculate the hybridization of each and everything. Did you get it? Everybody, if you have any doubts, you can ask me, and this session will go on a little quickly. Okay. And if you are finding my speed to be very fast, you can let me know, students. Okay. Now let's move on to the hybridization's next topic, which is what? Which is the electronegativity order. Correct? The most electronegative is your sp hybridization. It is which has a 50% of S character. It is the most electronegative carbon. For example, if C triple bond C carbon is present, this is the most electronegative carbon. Similarly, sp2 carbon is less electronegative and sp3 is the least electronegative carbon. Okay, understood the electronegativity. Now these were the basic things, and why did I discuss them? Look at this question. Look at this JEE Main 2021 question, asked basic question like find out the hybridization of carbon at A, B and C respectively. Answer this question. I'm looking at the chat box. What will be the answer to this question? Hybridization of A, hybridization of B and hybridization of C. What will be the answer? Speed, okay? Okay. Okay, I'm looking at the chat box. What will be the hybridization of A, bacha? A, can you see with this carbon, how many atoms are attached? 3 hydrogens and 1 carbon. It means 4 atoms are attached with carbon number A. Therefore, its hybridization is sp3. Similarly with B, how many atoms are attached to carbon? Only 1 atom, 2 atom and 3 atom. Correct? 3 atoms are attached to this B carbon. Therefore, for B, hybridization is sp2. Correct? And with C atom, C carbon atom, how many atoms are attached? With the C, how many atoms are attached? Like this is number 1, this is number 2, and this is number 3. Again 3. So its hybridization is again sp2. Anybody has any doubt in it? Correct. Correct. Now let's move on to the next question. See, these basic questions are asked in your exams. That's why I explained those things to you. Correct? Now we are going to look at the stability order. Now we have entered the real organic chemistry. This is where the real organic chemistry starts. Correct? The stability order of dienes, which you must know. What is the stability order, bacha? First of all, know the names of the dienes. This is called the isolated diene, which means what? Like the 2 double bonds are very far apart. Correct? Now this is the conjugated diene. Conjugated dienes means 2 double bonds are separated by just 1 single bond. This is called a conjugated diene, and accumulated diene means 2 double bonds are together. Okay? Now you have to know the stability of these dienes. So this cumulated diene is the least stable. It is not stable at all, never stable. Most stable diene is the conjugated diene, and in somewhere in the middle is the isolated. So this is the stability order which you must know. Again, a question was asked based on this stability order. Let us look at the question. Look at this question in JEE Mains 2022. Simple basic concepts. Can you see on simple basic concepts questions are asked? So now answer this question. Which of the following is an example of a conjugated diketone? Who can answer this question? I am looking at the chat box. Who can answer this question? Who can answer this question? It has asked about the conjugated diketone. Nobody is answering. Okay, nobody is answering. Beta, conjugated means what? The double bond must be separated by just 1 single bond. Correct? Now let us look at the C option. Can you look at the C option? Here a double bond is present here and it is separated by a single bond, and there again there is a double bond. Correct? Now here again there is a single bond and again a double bond, again a single bond and again a double bond. So can you see a double bond is separated by another double bond by one single bond. This kind of arrangement is called what? Conjugated arrangement, and that's the question. Which one is the conjugated diketone? So answer is your C. Easy peasy concept, right? So what concept did we start from? We started from this concept, right? Like conjugated means what, isolated means what, cumulated means what. Then you should also know the stability order of that, and based on this trick this question was asked. So can you see how the concepts are made into questions? So every question, every concept we are going to discuss in this lecture. Now let us move to this table of hydrocarbons. Hydrocarbons means what? Something which is made of carbons and hydrogens. Correct? And they can be acyclic or they can be cyclic. This is the first division. In acyclic division, they can be either alkanes, alkynes or alkenes, which you've already studied about. They can be homocyclic. Homocyclic means what? Ki only carbon is present in its entire cycle. Only carbon atom is present. It can be single bonded or it can even have a unsaturation in it, like a double bond or a triple bond, correct? Now heterocyclic compounds are also present, in which one carbon atom is replaced by another atom, any atom, nitrogen, oxygen, or whatever atom is replaced, correct? So this is the classification of hydrocarbons. Let us move to the very first concept again of nomenclature. We have discussed the basic things about the organic chemistry. Needed to know what is organic chemistry, move on to nomenclature. So before starting nomenclature, I am assuming that at this point of time, if your JEE is just around the corner, just a day to go, then you must know all the rules of nomenclature, right? You should be knowing the rules of nomenclature. I'm not going to discuss that. The only thing I'm going to discuss is the priority order of functional groups, correct? This is the very, very important order asked every year continuously in your JEE exam, okay? This is the order. For example, whenever you are naming any organic compound, the priority would be given in this order: carboxylic acid, sulfonic acid, ester, then your acyl halide, then your amide, then your nitriles, then your aldehydes, then your ketones, then your alcohols, then your diothiols, then your amines, then your double bond, and last comes your triple bond. Very important priority order. You all can take a screenshot of this. Okay? Now let's move on to the question. See, in 2022, a direct question was asked in JEE Mains, like the correct decreasing order of priority for the functional groups of organic compound. See, it has directly asked the priority order for IUPAC naming. Priority order for IUPAC naming. So I already discussed it that the priority order is actually option A. So you must know the priority order. It is very, very important. Correct? Now let's move on to another question. The correct IUPAC name of the following compound. Who can answer this question? I'm looking at the chat box again. Again, we are back to the chat box. Very good. Very good, A. Now we've moved on to the next question. Who is going to answer this? The next question, IUPAC name of this compound. See, again, JEE Main 2022 question. D. I have received first answer by Matti Pramesh D. Then I've received Praveen A, VK A. Nobody has given me the right answer yet. Why? This is a simple question. Extremely simple question. Nobody has given me the right answer. No. All of you are wrong. All of you are wrong. First, identify the main functional group. Main functional group, which is the main functional group here, this aldehyde. This is your main functional group, aldehyde. Therefore, rest are all what? Rest are all your not main functional groups. Okay? Now we are going to write the name of this compound. How many carbons are there? 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5, 6. 6 carbon chain is here, correct? 6 carbon chain is present, but we can also count this carbon. Can you see? The longest chain here is actually a 7 carbon chain, correct? Because right now NO2 is not our main functional group, correct? So NO2 will act as a substituent. So NO2 is a substituent. This ketone group is a substituent, correct? Now we are going to focus on the numbering. We have figured out the 2 substituents, the longest chain, and now the numbering. How we will number this? Numbering starts from the main functional group, which is your aldehyde. So this will be number 1 carbon, this will be 2, this will be 3, this will be 4, 5, 6 and 7. 7 carbon chain, correct? Now let me know the answer to this question. Now answer this question. I'm looking at the chat box. C. I've received answer C very many times. Correct. The correct answer is bacha C. 4. See, on 4th there is a methyl group. So I'm writing 4 methyl. On 6 number there is a nitro group. Then 6 nitro. And 3 number ketone group. And the ketone group, if it is act as a substituent, then a prefix is added. What is the name of the prefix? Oxo. So at 4, at 3 there is oxo. Hept 4e null. Correct? At fourth position there is a double bond, so 4e null. Correct? Easy. See, these kind of questions are also asked in your JEE main exam, so do not forget to do all these questions. Correct? Now let's move on to the next thing, which is the cleavage of bonds. I'm very sure you must all be very aware of this breaking of bonds. If there is a homolytic fission means what? Homolytic fission means the bond breaks right in the middle. One of the electron goes to A, the other electron goes to B, right? Homo means same fission. In this manner, free radicals are generated which are very reactive, which are neutral, odd electron species. You should know all these names. Free radicals are generated through homolytic fission which are very, very reactive, neutral species. Correct? Now let's move on to the next thing, which is your heterolytic fission. In heterolytic fission only you get a carbocation or a carboanion. Remember this thing, correct? In heterolytic fission you either get a carbocation or a carboanion, correct? Because here the bond doesn't break right in the middle, but somewhere, right? So either the electron go towards B or all the electrons go towards A. Right? So in the heterolytic fission, carbocations and carboanions are created. Correct? Now next, isomerism. Again, very important topic. Every year questions are asked from isomerism. Now what kind of isomerisms are there? There are actually three kinds of isomerism in your JEE main course. Number first is constitutional isomerism, which means what? Which means that the isomers have same formula but different bond connectivity, which means formula is same, like C3H6O, O2 will be the same formula, C3H6O will be same, but bond connectivity will be different. For example, it can either be CH3, CH2, CH2, OH, or it can either be CH3, CH2, OH and CH3, correct? So in both of them the molecular formula is same, but can you see here O bond is connected here, but here CO bond is connected at the second carbon. So bond connectivity is different in constitutional isomerism, correct? We are going to study each and type one by one, but let us focus on what kind of isomerism as a whole these are. The next kind is stereo. Stereo means what? The bond connectivity remains same. Here can you see the bond connectivity was different. But in stereo the bond connectivity is same. What happens? Their spatial arrangement is different. Like in 3D space they are arranged differently. The bonds are same. Correct? And these stereoisomers are actually of two types, enantiomers and diastereomers. What are these? We are going to study in detail. Okay? Wait with me. Next is conformational isomerism. Do not skip this topic. Every year questions are asked from conformational isomerism. What is this? These isomers also have what, bacha? Same connectivity. But these can interconvert into each other if some energetic barrier is overcome. And what are these? We're going to study in detail, but you must know there is three kinds of isomerism. Now let's study the first structural or the constitutional isomerism's first type, which is your chain isomerism. Every year questions are asked on this basic simple topic, so do not miss it. I know it's simple, but we have to do it, we have to revise it, because this 4 marks, simple easy 4 marks are very, very important. Chain isomers, what is happening in chain, bacha? Can you see this butane? Butane has the same molecular formula, C4H10, but I can write butane in a straight chain form and also in a branched chain form. So these both are what? Chain isomers. Similarly, in C4H8, which is an alkene, the alkene I can write as a straight chain isomer and also as a branched chain isomer, correct? Now you see one thing, here the double bond. Here the double bond is at the number 1 position. Here also double bond is at the number 1 position. Correct? So these are not position isomers. for this reason. Why? Because the double bond in the both the cases is at number 1 position. But these are chain isomers because this is straight chain and this is branch chain. So if this example comes in your exam, you will write them as chain isomer and not position, because this is a very confusing thing which I am already solving for you. Correct? Now next is a position isomer. In position, what happens, bacha? The position of mainly the functional group. Functional group can be any. For example, OH, COH, whatever functional group can be there, or your double bond and triple bond. Correct? These two are also your functional groups. The position of functional groups will change. For example, in C3H8O, this is propane 1-ol. Correct? All your alcohol is present at number 1 carbon. But in propane 2-ol, the alcohol is present at the number 2 carbon. So this is a position isomer. Here the position of the functional group has changed. Correct? Here at number 1, OH was present. Here at number 2, OH is present. Similarly, in C4H8. In C4H8, can you see? We have again come with the alkene example. Because alkene double bond is a functional group. Here double bond is at the number 1 position, but here the double bond is at the number 2 position. Now the position of the double bond has changed. Therefore, this is a positional isomer. But in the previous example, the double bond was at first carbon only, but the methyl group changed. Therefore, it was a chain isomer. No doubt should be there. Now this thing should be very, very clear. Now move on to functional isomerism. Functional isomerism means what? The functional group will change. Okay? In the previous, the functional group was same, OH, right? But here the functional group, bacha, will change. For example, the molecular formula I have written here is C2H6O. Correct? This can be written as an ethanol, or it can be written even as a ether. Can you see? This is an alcohol and this is a ether. Correct? As a ether, I can write it as methoxymethane. In both the cases, molecular formula is same, but functional group has changed. Here it is alcohol, here it is ether. Similarly, in C3H6O, can you see? The number first thing is the functional group here is aldehyde. Correct? And I can also write the same formula as a ketone. Correct? This is a ketone. So here what is happening? Molecular formula is same, but the functional group is changing. This is called what? This is called a functional isomerism. Similarly, C2H4O2. I can write this formula as an acid or even as an ester. This is what? This is the ester. This is the ester group. Correct? So I can write it as even ester group. So what is happening? The molecular formula is same, but the functional group is changing. Now you must know the pairs which show functional isomerism. Now you know the pairs like the alcohol and ethers can show functional isomerism. Then aldehydes and ketones show functional isomerism together, and your acid and esters show functional isomerism together. Correct? Now let's move on to the next, ring chain isomerism. Very, very important. What is happening in ring chain? You must have noticed that the general formula for an alkene is CnH2n. But this same formula applies for both alkene plus cycloalkene. This formula applies for both, bachcha. Okay? This same general formula, I can make an alkene out of it, or I can make a cycloalkane out of it. For example, what is the general formula of this propene here? Here C carbon atoms are 3. Can you count the hydrogens with me? Hydrogens are 3 plus 3 is 6. Correct? So hydrogens are 6. Similarly, the molecular formula for even cyclopropane is C3H6. Correct? So with the same molecular formula, I can make either an alkene or a cyclic compound. Therefore, this is a ring chain isomerism. This kind is called ring chain isomerism. Correct? Now next question is metamerism. Very, very important. Very, very important kind of isomerism. It is asked every year. Every year continuously this on this metamerism questions are asked. Beta, what is happening in metamerism? The molecular formula is same. Always remember, in all these kinds of isomerism, molecular formula remains the same. In this, even the functional group is same. Functional group is also same. Molecular formula is also same. But what is happening? What is happening, bacha, here is the alkyl group around the functional group is changing. For example, with examples you will understand. This is an example of ether, right? This formula is of an ether. Even this formula is of an ether, and this formula is also of an ether. Correct? So can you see in this ether compound, in all these ethers, number of carbon atoms are 4. Correct? So molecular formula is same for all these three. But what is happening? The alkyl group arrangement around the oxygen atom is changing. Can you see here around the oxygen atom 2 ethyl groups are present. Correct? But here what has happened? 1 methyl and 1 propyl group. And here what has happened? 1 methyl and 1 isopropyl group is added. Right? So the molecular formula is same. The functional group is also same. All are ethers. All have the same molecular formula. But what is happening? Around the functional group, which is your oxygen, the arrangement of the alkyl groups is changing. Correct? Here 2 ethyl groups. Here 1 methyl propyl group. Here 1 isopropyl, 1 methyl group is added. So what is happening? Position of alkyl groups is changing. Nothing else is changing. So this kind of isomerism is called what, bacha? Metamerism. Correct? And you have to note this thing, that only and only ethers, only and only ketones, only and only secondary and tertiary amines, and your esters can show what? Metamerism. Which means what? Any functional group which comes in middle of the chain. Can you see ether is coming in middle of the chain? Correct? And even your ketone, how do you write ketone? Ketone always come in middle of the chain. Correct? So any functional group which comes in middle of the chain, and it can never be terminal functional group. है ना? It can never be at the end of the chain. Such kind of functional groups will always show your metamerism. Any doubt in this? Any doubt in this? Any doubt in this? Okay. No doubt. I'll move forward. This is metamerism example. Now tautomerism. Again, very, very important. Asked every year. These two are favorite of your what? Examiner. Tautomerism, what is happening? I will teach you tautomerism in the easiest format. In keto-enol tautomerism, what is happening? This is a ketone group. Correct? In the ketone group, what we are seeing in, this is the functional group keto, right? This is the functional group keto. So the carbon next to the functional group is called what? It is called the alpha carbon, right? This carbon is called alpha and this carbon is also alpha. Both are alpha carbons. So what is the condition for keto-enol tautomerism? The condition is the alpha carbon should have what, bacha? Should have alpha hydrogen. Correct? The alpha carbon should have hydrogen. Only then keto-enol tautomerism will happen. And what happens in keto-enol tautomerism, bacha? This hydrogen migrates to oxygen, correct? And this double bond comes here. This only happens, this is the easiest trick to remember keto-enol tautomerism. One hydrogen will migrate there and the double bond will break and this will form a alkene kind of thing. Propene 2-ol will be formed. Okay. Now you must be asking me ki ma'am, which is the most stable form, bacha? The most stable form in most cases is your ketone. Keto thing is 99% found and this is only like 1% form. Correct? So enol form is not that stable. Keto form in most cases, this is again chemistry. It is filled with exceptions. Correct? So, but in most cases, according to your syllabus, you have to remember that keto group is the most stable kind of, and this, bacha, this represent what? This sign represent equilibrium. 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 Okay. So keto form is most stable form. Now let's move to the question. Question asked in 2021 JEE Main exam. Which of the following show is an example of metamerism? Easy question. Which of these following show metamerism? Can anybody answer? I'm looking at the chat box again. We are back at the chat box. We are back at the chat box. Stop chit-chatting, bacha. Answer this question. Answer this question. I am looking at the chat box. D. I've received answer D by Shreya A. Kulkarni. Very, very good, Shreya. Answer is actually D. Then shoot out G. Okay. Then I've again Madhulika, Akashaya. Madhulika, you're wrong, bacha. Sanjay, Alvin. Very, very good. Now everybody is correct. The answer is bacha D. Can you see? Metamerism means what? Metamerism means same molecular formula, same functional group, but the alkyl groups change around the functional group. For example, in D, this is a ketone functional group. This is again a ketone functional group, right? Here only two methyl groups are present. Ethyl group is present, but here see the arrangement of alkyl groups is different, but the molecular formula remains the same. So answer is D. The arrangement of alkyl atoms is changed. Now you understood, right? How important this is. Now let's move on to the next. Compound. Again JEE Main 2021 question. Compound with the molecular formula C3H6O can show. What kind of isomerism can this formula show? We've discussed the same thing with example. Who can answer this question? Who can answer this question? D. I'm answering D, functional group. Okay, Madhulika, what confusion is there? Ask me, I will explain. I'm here to explain. I'm here to explain. B, both positional and metamerism, somebody is saying. D, B. I'm receiving mixed answers, bacha. C3H6O can only show one kind of isomerism. And which is which, bacha? Functional group isomerism. This kind of isomerism, it can only show, it can either form an aldehyde or a ketone. There is no other possibility. No other possibility with this formula. And how you will come to know? Only when you take out your pen and paper and try to draw the structure. Try to draw the structure with every carbon, every hydrogen, every oxygen. Only then you will get the right answer. See, organic chemistry is exactly like your physical chemistry. Like you cannot just look at the formula and predict its structure. No, you have to take out your pen, paper and draw, and then only you will get the right answer. Okay. So the only structure possible through this chemical formula is either or aldehyde or a ketone. And we know aldehyde and ketone means what? Functional group isomerism. Correct? Beta, in metamerism, Madhulika is asking ki ma'am, I am not understanding metamerism. Beta, I have explained metamerism very, very clearly. You can go back and understand. See, in metamerism, I am again explaining to you. In metamerism, what is happening? This is your what? The functional group ether. So around ether functional group, which is your oxygen, around this oxygen, the number of alkyl groups. Can you see? This is alkyl group. This is again alkyl group. So the number of alkyl groups is changing, which means the arrangement of alkyl groups. Here, 2 ethyls are present. Okay? Here what is happening? 1 methyl and 1 propyl is present. Here what is happening? 1 methyl, 1 isopropyl is present. So molecular formula remains same. Functional group is also same, ether in all the cases, correct? But the arrangement of alkyl groups is changing around that functional group. So this is called metamerism. This kind of isomerism is called metamerism. Okay. Now next question is this. Match list 1 with list 2. Again, see JEE Main 2023 question. Can you see? On these basic simple isomerisms, so many questions are asked every year. I've shown you a question from 2021, 2022, 2023. Can you see how important this topic is? Now tell me the answer. Propanamine and N-methylethanamine. What kind of isomerism will it show? Hexane 2-on and hexane 3-on. What kind of isomerism will it show? Can anybody tell me? Now you can do this question, correct? You can do this question. I can give you such questions as homework, so we don't waste any time because I've explained each and everything to you, all kind of isomerisms to you. Correct? For example, hexane 2-on and 3-on means what? Means what? It is positional isomer. है ना? Ethanamide and hydroxyethanamine, which means what? And orthonitrophenol and paranitrophenol, which means what? So these all things you can actually D2B1. Okay, let us look. This is the answer. This is the answer. This shows functional isomerism. Were you guys correct? Were you guys correct? For example, this is primary amine and this is what, bacha? This is a secondary amine. So these are functional isomers. Correct? Now let's see metamers. Metamers, what is happening? This is a ketone group here and here it's the hexane 2-on and 3-on. These are metamers. See, around this functional group, what is happening? Around this functional group, arrangement of your alkyl chain is changing, nothing else. Correct? So these are metamers. Now let's look at tautomers. Tautomers, what is happening? This is a amide and this is a E-mine. है ना? E-mine. So what is happening here again? What is happening? This hydrogen is migrating to the oxygen and this double bond is coming over here. So this is showing again a kind of tautomerism. Then positional isomers are actually this. This is positional isomers. Ortho and paranitrophenol. Okay. Next, let's move on. Beta, you will get the session PDF on the Telegram channel. After this session is over, join that Telegram link and I will upload the entire PDF. This contains homework questions also at the end, which you can do and practice. Now let's move on to the next, which is stereoisomers. We have done structural isomerism, in which what was happening? The bonds were different. The arrangement of bonds were different. In stereo, the arrangement of bond is same. Okay, bonds remain the same, but what is happening here? The arrangement in the space is changing. Correct? Now, for example, number first is geometrical isomerism. Geometrical isomerism is just of this type, cis or trans, and even we can write EZ isomerism. EZ or cis or trans is the same thing. Correct? Cis means what? Cis means same functional groups will be on the same end. So for example, this is a cis butene and this is a trans, which means same functional group will be on the opposite end. It means trans. Easy? So this is trans, but this is cis isomer. Okay? And then next EZ is also the same kind. EZ is also cis trans only. Next, we will do geometrical isomerism. How to calculate the number of geometrical isomers. Recently, these questions haven't been asked in very recent years. So now there's a probability that in 2024, this can be asked. Okay. So how to calculate the geometrical isomers? This is the formula. Like in case of symmetrical alkene, bacha, what happens? Number of geometrical isomers is 2 to the power n. But in case of unsymmetrical alkene, okay, what happens? Number of geometrical isomers is 2 to the power n minus 1 plus 2 to the power p minus 1. Okay, n here denotes what? N is number of double bonds. Number of double bonds. Correct? N is number of double bonds. Okay. Now, if n is even, if even number of double bonds are present, then p, the value of p will be n by 2, and if odd number is present, value will be p n plus 1. I cannot help it. You have to learn this formula, take a screenshot of this, or you will receive the PDF in the Telegram channel. Okay, very, very important slide. Now, let's move on to the next question. The question asked in JEE Mains 2020, which of the following compounds show Geometrical isomerism. Such easy question. Can you see? It is just asked which will show geometrical isomerism. Which means what? Which will show a cis and a trans structure. That is it. Which will show geometrical isomerism. Does anybody know answer of this question? Does anybody know? Beta, hex 3-on and hex 2-on is a metamer. Sorry, that was my slip of tongue that time. It is not positional, it is a metamer. Hex 3-on and hex 2-on is a metamer. Okay. Positional was the nitrophenol, ortho and para. Okay. Now answer this question. Answer this question. Do not fight in the chat box, bacha. B answer. Somebody has given that B will show geometrical isomerism. B, D, Sanjay has given D. Sanjay, you are absolutely correct. Then Harshad Ram is absolutely correct. Then Shreya is absolutely correct. The answer is bacha D. D option is correct. 4-methyl pentuene. See, this will be the structure. Can you see the structure of E? E means what, bacha? E means the trans form. E means trans. Okay? And Z means cis form. Okay? So in trans form, can you see here? Around this double bond, this is the double bond. So around this double bond, we have to look at the arrangement. So can you see around this double bond, one CH3 is downwards. Can you see? Here this CH3 is bacha downwards and this whole cheese is upwards. Correct? So this is a trans form. And in the cis form, what is happening? Around this double bond, I can write methyl group downward and this other group also downward. So now the similar groups are at downward position. Therefore, this is a cis isomer. But here the methyl groups were opposite. Opposite means trans. Correct? This is only possible in your fourth option. In your fourth option. Okay? And how you will come to know about that? Only and only when you draw structures of this. If you do not draw structures, your answer will be wrong. You just cannot look at the formula and tell me that this will show and this will not show. Correct? Draw these structures. Use pen and paper. Next. Next, we are back to optical isomerism. We have done geometrical. Geometrical means what? Either cis or trans or E or Z. Optical means what, bacha? The condition for optical isomerism. Optical isomerism can only be detected by PPL light. You must be aware of this. Plane polarized light, if it moves to the D direction, that is the right direction, or the L direction, which is the left direction. Okay, that is only experimentally seen. Okay, you cannot look at the compound and tell me that this is what kind of compound, D or L, dextrorotatory or levorotatory. Okay. Now, what are the conditions for optical isomerism? The condition number 1 is there should be a presence of chiral atom. Chiral atom means what? That the carbon should be attached to 4 different functional groups, A, B, C and D. 4 different functional groups it should be attached to. Number 2, no symmetry. In the entire compound, no symmetry should be present. Plane of symmetry, no plane of symmetry, no center of symmetry, no diagonal symmetry, no symmetry should be present. C is non-superimposable mirror images. Examples, look at the examples. For example, these are enantiomers. Enantiomers means what? For example, the chlorine here is attached to a wedged hand, but here it is, the chlorine is attached to a dash head. So therefore, these are called enantiomers. Understood? Now let us look at diastereomers. Diastereomers means what? These are not mirror images. Not mirror images. Therefore, okay, not mirror images of each other. For example, look at this compound. Is this compound a mirror image of this compound? No, because here only one is in dash position, the other one is in wedge. Here both are in wedge position. Okay, so these are not the mirror images of each other. If any compound is not the mirror image of each other, that is called a diastereomer. Now, what is the difference, bacha, here? Now, I am again explaining it to you. Can you see here that the chlorine is attached to this atom only, correct? and here also the chlorine is attached to this atom only, correct? But what is happening? The arrangement in space is different. Here the chlorine is towards us, towards the user. Wedge means what? Towards me, I can see it. And this dash chlorine means what? It's away from the user, correct? It means what? The position or the spatial arrangement. The arrangement in space of the chlorine is different, but the bonding is same. Can you see? Here also chlorine is attached to this carbon. Here the chlorine is attached to this carbon. In diastereomers also, can you see that the chlorines are attached to the same kind of carbon, only their position is different, correct? In enantiomers, they are mirror images. In diastereomers, they are not mirror images of each other. Okay, let's move on to the next example. For example, these are your enantiomers. Enantiomers, why am I saying? Look at the bromine here. The bromine here is present at a wedged hand. But in this example, the bromine is at the dashed hand. Okay. Now again look at the hydrogen here. The hydrogen here is at the wedged hand. But here the hydrogen is at the dash end. Correct. So here the position is again changing. Correct. So these are mirror images of each other. These are called enantiomers. So in mirror images, what is basically happening? That the wedged hand is becoming dash and the dash hand is becoming wedge. If only that is happening, then that one is a mirror image called a enantiomer. But in diastereomer, can you see? For example, in diastereomer, here the bromine is at the dash hand. Here also the bromine is at the dash hand. Here the hydrogen is at the dash hand, but here the hydrogen is at the wedge hand. Can you see? Now here the arrangement is not totally opposite. Correct? These two are not mirror images of each other. Correct? Because for this to become a mirror image of this, the hydrogen, if the bromine, see the position of bromine is not changing, only the position of hydrogen is changing. Therefore, both the positions are not changing. Hai na? So therefore, these are diastereomers. Are you understanding what I am trying to say? Are you understanding? Next, we are back to doing the question. The number of stereoisomers possible for 1,2-dimethyl cyclopropane is. Who is going to answer this question? Who is going to answer this question? The number of stereoisomers. Stereoisomers means what? Bond arrangement will be same, only the spatial arrangement will be different. Correct? The number of stereoisomers for 1,2-dimethyl cyclopropane. I am looking at the chat box. I am looking at the chat box. Nobody is answering me. Nobody is answering me. B. Sanjay has given B answer 4. 4. That is the wrong answer. Wrong answer. Wrong answer. B. Wrong, wrong, wrong. See, here the answer is actually 3. This is the structure of 1,2-dimethyl cyclopropane. So this is one of the structure. Correct? Where both the methyl groups are at the what position? Upward position. Can you see? Can you see? Here both the methyl groups are at the upward position. Okay. Now in this, why there are not 4 isomers, bacha? Can you see that when I'm writing methyl group at the top position and in the cis format, what is happening? I am receiving a what? I am receiving a plane of symmetry. Can you see? Can you see? If I cut this compound in the middle, I receive a very symmetrical compound. Right? So therefore this compound, bacha, is not optically active. Okay? This is one structure, but this will not form an enantiomer. Okay? This cannot form a mirror image of each other because this is not optically active. Right? But if I write methyl groups here like this, here these can form an enantiomer. Right? So therefore 3 stereoisomers are present for this compound. So you have to look even for plane of symmetry. Now this will not form, it's another mirror image. Correct? Everybody got it? Everybody got this? Okay? Everybody understand? Okay, which of the following molecules does not show stereoisomerism? Again, the similar kind of question. Which do not show stereoisomerism? Which do not show stereoisomerism? Now, how to approach this question? The answer is 3-ethyl hex 3-ene. Why? Now, let us look at all the structures. Now, let us look at all the structures one by one. Correct? Now, let us look. One of the option was 4-methyl hex 1-ene. So, this is the structure of 4-methyl hex 1-ene. Can you see there is presence of one chiral carbon? Correct? So, this will show your isomerism, optical isomerism. Correct? Now, in the second is 3-ethyl hex 3-ene. In 3-ethyl hex 3-ene, there is cannot show geometrical isomerism. This cannot show geometrical isomerism. In this, there is no, bacha, there is no what? In this, there is no chiral center, first of all. In this formula, there is no chiral center, and also it will not show cis or trans isomerism. Correct? Now, in the third option, can you see? Here the double bond is present. Correct? So, this double bond now has methyl groups on both its ends. Now, this can show geometrical isomerism. Hai na? This one bacha can show geometrical isomerism. Now, in the fourth compound also it has one chiral center. Can everybody see? So, this will again show stereoisomerism, and I have already told you that geometrical isomerism is also a kind of stereoisomerism. So, this will show stereoisomerism, this will show stereoisomerism, okay? This will not show stereoisomerism, and even this will show the stereoisomerism due to the presence of a chiral carbon. So, what you have to look for? Either there should be a presence of chiral carbon, which means to one carbon atom, 4 different groups should be attached, and the next thing you have to look for geometrical isomerism, cis and trans. Can that molecule show cis-trans isomerism? Because this can show, but this cannot show. Right? Right? Can we move to the next part, bacha? Okay. Now we are moving and we are learning RS nomenclature. Now let's learn the RS nomenclature. Again, a very important kind of optical isomerism. In this, like this kind of nomenclature questions are asked every year. Even in 2023, a very interesting question was asked from RS nomenclature. We will discuss that. What happens? How are you going to predict whether your compound is R or S? So what is the meaning of R, bacha? R means clockwise, and S means anti-clockwise. Correct? Now what do I mean by that? Let us look at example one by one. Correct? Now let us look at example one by one. For example, whenever we have to do RS nomenclature, bacha, we have to give numbering. We have to give numbering to each and every atom attached to the chiral carbon. First, look for the chiral carbon and then look at each atom attached. Now we have to start numbering those atoms, and start how we have to number? By looking at their atomic number. So whichever has the highest atomic number will get number 1. For example, here bromine has the highest atomic number, then chlorine, so this will get number 2, then your then your carbon, right? Then your carbon, which will get number 3, and then your hydrogen, which will get the number 4th position. So this is how you will start numbering this. Are you understanding? First select the chiral carbon and then start, okay, you have selected the chiral carbon, then start numbering all the substituents around it according to their atomic number. Highest atomic number gets number 1, then 2, then 3, then 4. ठीक है, first step is complete. In the second step, what you have to do, for example, now what you have to do, you have to start rotating your pen from how? You have to start rotating your pen in this direction, number 1, from number 1 atom to number 2 atom to number 3 atom. This is how your pen should move. For example, I start from bromine because bromine is the number 1 atom. Then number 2 atom is chlorine, correct? So now my pen will move from 1, 2, 3 like this. Can you see how my pen is moving? Correct? So my pen has moved in what direction? My pen has moved in the clockwise direction. Can you see? This is how a clock moves. Correct? This is how a clock moves. This is the clockwise direction. Therefore, this, the nomenclature for this will be R. R nomenclature. Easy? Easy or not? Correct? So, we have given R nomenclature to this. The point to note in this kind of nomenclature is that the atom which has to get the last position, the number 4, which will mostly be hydrogen, correct? So, whichever atom is getting the last position has to be on which end? Dashed end. ठीक है, last position should always be given to the dashed atom. ठीक है, only then you can correctly predict the nomenclature of this. So, but does everybody understand how to give naming to this kind of nomenclature? We are going to discuss other kinds also. This thing is clear or not? Is this thing clear to everybody? Okay. Now let's move on to the next. So we have already discussed that this were a R kind of nomenclature. But now what happens, bacha? Now what happens if, now look at the B option. Can you look at the B option? Now start, now give me the nomenclature of the B part. So again, bromine will be number 1, correct? Chlorine will be number 2, methyl will be number 3, and hydrogen will be number 4. Correct? And the last position wala atom, which is hydrogen, is on the dashed end. So therefore, this is the correct kind of numbering that we can do. Now start moving your pen in 1, 2, 3 direction. So now if I move the pen in 1, then 2, then 3 direction, then what direction am I getting? I am getting an anti-clockwise direction. Therefore, the nomenclature of this compound will be S. Correct? Correct? Now let's move on to the next. Now what happens if your lowest number, for example, here hydrogen will get the lowest number, right? Now if that lowest atom is actually not on the dash position but on the wedge position. Now what will you do? Now how will you name the compound? Very easy again. Now what you have to do, bacha? Again start by numbering each and every atom attached to the chiral carbon. So here fluorine gets number 1. Then oxygen gets number 2 and your carbon gets number 3 and hydrogen gets number 4. I've already numbered, correct? Now what I do? Now my next step is to move my pen from 1 to 2 to 3, correct? This is my next step, right? This is how I move my pen. So I move my pen from 1 to 2 to 3, correct? This is how I'm moving my pen. Now can you see how my pen has moved? My pen has moved again in the anti-clockwise direction. So this compound, because my pen has moved in the anti-clockwise direction, this compound must be named S. But no, can you see the hydrogen is at the wedged hand. It is not at the dash hand. है ना? The hydrogen, the lowest priority atom is not at the wedged hand. Therefore, we reverse its configuration and it becomes, the correct configuration is actually R. So what I am doing, so whenever I find the hydrogen at the lowest priority atom of the hydrogen at the wedged position, then what do? I do nothing. I again follow the same technique which I was following. Number each and every atom according to their atomic number. Like fluorine gets 1, oxygen gets 2 and carbon gets number 3. Correct? Now again I move my pen in 1, 2, 3 direction. correct? From 1 to 2 to 3 direction. Now whatever direction I'm getting, I just need to reverse it. I just need to make a chain. So R will be the correct answer. Does everybody get this? Does everybody get this? Okay. Now what happens, bacha? Now we have discussed when the hydrogen was at the dash position, and we have also discussed when hydrogen was at the wedge position. But what happens, ma'am, if the hydrogen is at similar bonding position? If the hydrogen is at the plane of the page, for example, this compound, what will happen here? Nothing, don't worry about it. So whenever your hydrogen or the lowest priority atom is in the plane of the paper, what you have to do, you just have to replace, you just have to exchange it with any atom which is present at the dash position. Just take this hydrogen, see, replace this hydrogen with this methyl group. So bring this methyl group here and take this hydrogen to here. So now what we're getting? This structure. We're getting this kind of structure where hydrogen is again at the dash position and methyl is at this position. Correct? Correct. So we have done one kind of exchange. Only one exchange we have done, right? So we have exchanged this methyl atom with this hydrogen because we always want the lowest priority at the dash position. Okay? That's why we have made this exchange. So after this exchange, follow the same process. Again, start numbering the compounds, numbering the atoms. The number 1 goes to again fluorine. The number 2 goes to oxygen. Number 3 goes to methyl. And number 4 goes to hydrogen. Now again move your pen. Start moving your pen in 1 to 2 to 3 direction. So this is fluorine number 1. Then oxygen number 2. And your methyl number 3. So can you see in what direction my pen moved this time? My pen moved this time in the clockwise direction, which is the direction R. Correct? But again, because the hydrogen initially was at the plane of the paper, right? And I've made only one exchange. Therefore, the R position will change into S. So the correct answer will be the reverse of the direction which you got using this. So the correct answer is actually S. The correct answer is actually S. Correct? Now, do you have any problem in RS nomenclature? You can ask me. I've explained each and every kind which can be asked in your exam. Each and every kind we have discussed. Beta, this is an English channel, so I cannot explain in Hindi. For Hindi, we already have one channel which is called Vedantu JEE. You can go and see Pahul sir's lecture on it. Okay? Beta, it is visible. It will be visible when you get the PDF. Okay? Everybody understood? I'm moving on to the next. So I've already made you understand all these things. Now we are back again to a JEE Main 2023 question. See, this question is again based on your RS nomenclature. Okay? In RS nomenclature, I'll tell you again one more very, very important thing. So here the question is, 2 statements are given. Number 1 statement is this compound is optically active. Okay, now you have to tell me whether this compound is optically active. Is this statement true or false? Okay, now let us look at this compound. Can you see this carbon? So this carbon is actually attached to 4 different things, right? Is this carbon optically active? You have to look at that carbon and tell me, is that carbon optically active? What is your conclusion? I'm looking at the chat box. I am looking at the chat box. I am looking at the chat box. Bacha, please don't look at whatever chit chat is going on in the chat. If you are a student who is studying with me, you ask your question in the chat box. I will answer it. I will answer it. Okay. Now, what do you think about this? Is this compound, is this carbon chiral? That carbon which I have made a red dot on it. It is optically active. Yes, yes, very good, very good. I have received correct answer. And bacha, why is it optically active? Now you can argue, ma'am, here here, can you see this carbon, around this carbon, one hydrogen atom is present, correct? One NO2 atom is present, which is also correct. But these two groups, can you see the other two groups? The other two groups, bacha, are what? The other two groups which I am seeing are actually just alkenes and similar kind of alkenes. Can you see? These are same alkenes, but there is only one tiny teeny difference. The tiny teeny difference is what? This is bacha a cis alkene and this is bacha a trans alkene. Even though they are same kind of alkenes, they are made up of how many carbons? 1, 2, 3 carbons. Here also it is made up of 1, 2, 3 carbons, है ना? And the placement of double bond is also same. But their geometry is different. This is cis alkene and this is trans alkene. Can you see? So because a cis and a trans alkene is attached to it, even though they have the same structure, this carbon is chiral, so therefore this is optically active. This is a true statement, correct? Now for this carbon, for this compound, we will calculate, bacha, what? We will calculate the RS nomenclature. ठीक है? RS nomenclature we will calculate. Now how you will calculate RS nomenclature? For that we have to start numbering each and every atom. This atom is number 1. है ना? Should I give nitrogen number 1? Yes. This is number 1 and hydrogen will get the number 4th position. Okay, ma'am. Now, ma'am, what will be the number 2 and the number 3 position? Because these are both exactly same compounds. Here it is also carbon, here it is also carbon. And then again if I move forward, again carbon, again carbon, again carbon, again carbon. Now, ma'am, how we will number it? So, bacha, always remember in this numbering, cis is always numbered higher than your trans alkene. Always remember. Cis alkene is always numbered higher than your trans alkene. Therefore, this side, this which is your cis alkene will get the number 2 position and which is your trans alkene, it will get the number 3 position. Correct? Now let's start. Now tell me whether this compound is R or S. Is that compound an R compound or an S compound? So let me come here. Okay, now this is a better structure, better representation, correct? If you are not able to understand in that slide, so you will understand using this slide. So as I told you, this will be number 1 NO, the number 4th will be given to hydrogen, number 2 will be given to cis alkene and number 3 will be given to trans alkene. Now what do? I move in which direction? I move in 1 to 2 to 3 direction. So if I move from 1 to 2 to 3 direction, what kind of direction I'm getting? I'm getting an anti-clockwise direction. So therefore this alkene is bacha S alkene. Similarly, the next part of your statement is what? In the next part, it has asked whether this compound is a mirror image of this compound. So we have already calculated that this compound was actually an S compound. Okay. So for this to be a mirror image, this has to be what? For a mirror image, that has to be an R compound, correct? Because S and R are mirror images. So you have to tell me whether this is also a R compound or an S compound. So how we will calculate? Again same thing. Here N will be given number 1st position, hydrogen will be given number 4th position, okay? And here cis alkene is this one. This one is cis alkene. Cis alkene will be given number 2 position and trans alkene will be given number 3 position. Now move from 1, 2, 3 direction. Now if I move in 1, 2 and 3 direction, what kind of direction I'm getting? I'm again getting an anti-clockwise direction. Therefore, the configuration of this compound is again S. So because both the compounds are in S configuration, these are not mirror images of each other. So therefore, statement 2 is bacha false. What kind of statement? False statement. Correct? Everybody got this? Yes, bacha, Cis, see I have given, this is cis alkene, I have given number 2 to, beta, it's not about that. It's not about that, Alvin. Number 2 means what? It's the priority number. Like I'm giving the first priority to nitrogen. Then I'll give the second priority to cis. Cis will get the second priority. Trans will get the third priority. And fourth priority will be given to hydrogen. Hydrogen is least prior. Okay? It is based on that funda. Okay, everybody understood this? Did everybody understand? If you did not, you can use these notes to understand it even further, because I've already told you each and every nook and crook in detail, and you will understand it better once you write it with pen and paper on your own. Correct? You will understand it even better. Okay, somebody is asking, ma'am, how do you know which one is cis and which one is trans? Amazing, interesting question. So, bacha, can you see what is the meaning of cis? Cis means around the double bond, both the atoms are in the same direction. Correct? That is a cis alkene. This is a cis alkene. Anybody has any doubt in this? And what is a trans alkene? Trans alkene means around the double bond, one methyl group is upwards and the other methyl group is downwards. That is a trans alkene. Now can you tell me in this structure, this methyl group and this methyl group are both in the upward direction. Can you see? So this will make this alkene as cis. Correct? Now around this double bond, can you see? One methyl group is in the, yes. Around this double bond, one methyl group is going to that direction and the other methyl group is going to this direction. Can you see? Both the methyl group are in opposite direction to the double bond. Therefore, this one is trans alkene. While this one, both the alkyl groups are in the same position. So cis, because here around the double bond, the alkyl groups are in the opposite direction. So trans. Everybody understood this concept? Everybody understood? Okay. Next, conformational isomerism. Very important kind. Every year questions are asked on this kind of isomerism. It is very easy, extremely easy. You don't have to do anything. Okay. In conformational isomerism, bacha, what happens? What happens is, this is your one carbon. So here I have taken the example of a butane. I have taken example of butane. Butane is made up of 4 carbon atoms. Correct? So if I want to make conformational isomers of butane, what I'll do? I'll need 4 carbon atoms. And how are those 4 carbon atoms represented? One carbon atom is represented by a dot, which is in the front. The dot is in the front. And this circle, can you see? This circle, this entire circle represents another carbon atom. This entire circle represents second carbon atom. Correct? Now to these 2 carbon atoms, another carbon atom, number 3 carbon atom is attached to the dot and number 4 carbon atom is attached to the circle. Correct? Now visualize this picture in your head. What I have done, this is your butane molecule, C. Correct? Butane has 4 carbon atoms. Correct? Now focus on the middle 2 carbon atoms. If I am focusing on the middle 2 carbon atoms, I made one carbon atom, for example, this one as a dot. I have made this one the dot and I have made this one an entire circle. Correct? Now what is happening to this dot? One carbon is attached. So to this dot, I have attached one carbon. Can you see? One methyl group is attached to the dot. Similarly, to this circle again, this carbon atom is attached. Can you see? So to this circle, I have attached another methyl group. So this is how you represent a butane. This is how you represent a butane and form its conformational isomers. Is this thing clear to everybody? Is this thing clear to everybody? Okay. Now what is happening? Now this arrangement can be written in various forms. Various forms means what? When both the methyl groups are exactly behind each other, exactly behind. So here most repulsion will happen. For example, both the methyl groups are behind each other. Here both the hydrogens are behind each other, and here also both the hydrogens are behind each other. So this experiences bacha what? Most repulsion. Most repulsion means what? This is the most unstable compound. Okay, if this is unstable isomer of conformational isomer is called what? Eclipsed. Eclipsed isomer. And this one is fully eclipsed means what? That both the methyl groups are exactly behind each other. All the hydrogens are exactly behind. All the hydrogens are exactly behind each other. So this experiences most repulsion, most unstable conformation. Next is your Gauche. Now Gauche means what? It is somewhat stable. Somewhat stable conformation, because look at the methyl groups here. Here the methyl groups are actually 60 degrees apart. Correct? So it doesn't experience that much repulsion. Okay. So this is somewhat stable. So stable conformation is called Gauche or staggered conformation. Okay. Now we are again back to eclipsed. Eclipsed can be of this type also, where the dihedral angle. Here the dihedral angle between methyl is 0 degree. Here between methyl is 60 degree. Here again the dihedral angle becomes 120 degree. But can you see here? Methyl and hydrogens are exactly behind each other. Here also methyl and hydrogens are exactly behind each other. So this is again a eclipsed. It means unstable conformation. Eclipsed means unstable. If I am exactly behind another atom, I will experience a lot of repulsion and I am unstable. But if I am at an angle, can you see here? Methyl are apart. Here hydrogen are apart. So here what is happening? Because they are apart from each other, they are distant from each other. So minimum repulsion. So this is somewhat stable. This is unstable. And again look at this. This is the most stable conformation. Most stable conformation in which the dihedral angle. This is called the dihedral angle. Okay. When the dihedral angle between two methyl molecules is what? 180 degree. They're exactly opposite to each other. If one methyl is here, another methyl is down. Correct? So this is the most stable atom. Can you see? This is bacha the most stable configuration. Next, now look at this energy diagram. Asked many times. Energy diagram. See, the highest energy. The highest energy means what? See, I am writing here. Whenever energy is high. Whenever energy is high, that compound bacha is what? Unstable compound. Okay? So we have to focus on where the energy is low. If the energy is low, the compound is bacha very stable. Okay? For example, here, this is again a eclipsed conformation. I told you this experiences maximum repulsion. So this has the maximum energy. It means it is unstable. Correct? Now look at this Gauche conformation. Can you see this Gauche? Where the dihedral angle is actually 60 degree. 60 degree is this kind of stable. It is lower energy but not that lower. Lowest energy is when the dihedral angle bacha is how much? Between the two methyl groups is 180 degree. It means it is the most stable compound. Most stable Gauche conformation. Okay. Again, can you see eclipsed conformation where the angle between them is 120 degree, has high energy but lower energy than the fully eclipsed conformation. So this is how the energy diagram flows. Okay. Does anybody have any doubt? Lowest energy is of this compound where the dihedral angle is 180 degree. Highest energy is of the fully eclipsed conformation. Correct? Anybody has any doubt in this energy diagram? Anybody? Correct. Okay. Next, let's go. Arrange the following conformational isomers of N-butane in order of their increasing potential energy. See, whatever I've taught you, everything I'm teaching you right now is extremely, extremely important. This is JEE Main 2021 question. Can you answer this? Can you answer what is the... Okay, answer. Give me the answer to this question. So which one has the highest energy? Which one will have the highest energy? Which is the most unstable conformation will have the highest energy. Okay, now I am back to looking at the chat box. Answer this question. Answer. Beta, Gaurav Thalanki, I cannot reduce the brightness right now, but for next sessions, I will keep that in mind. I'm sorry if something is not visible. You can always download the notes. Okay? After this session, you will get them. Download them and look at the notes, and then again listen to whatever if you didn't understand and you're not able to see right now. Okay? You can do that later on. Okay, I have received first answer B, D, Praveen, Vikram, Srinivas, C, D. बहुत mixed answers are here. So let us look at actually the answer is D. So whoever answered D, bacha, you are correct. You are absolutely correct. So the maximum energy means most unstable configuration which has the most repulsion. So most repulsion is in the second compound. Can you see the second compound? This has 0 degree angle, correct? So this is the most unstable, so highest energy is second. Now let us look at the fourth. Fourth, can you see? Fourth, here what is happening, bacha? This CH3 is right behind this hydrogen. This CH3 is right behind this hydrogen. And also these CH3s are very close to each other. Therefore, this has the second highest energy. Now let us look at the third diagram. Third is this. Third, can you see? Here, even though CH3 and CH3 are at 60 degree, but they still experience some repulsion because first is what, bacha? First is your most stable configuration where the CH3 is at a 180 degree, 0 repulsion. Most stable configuration is first. So this one will have the lowest energy. Okay. Now and then the 60 degree angle will have a little higher energy. Then fourth and then second, because in here 2 methyl groups are right behind each other, but here methyl and hydrogens were right behind each other. Correct? Everybody understood this question? Does anyone have any doubt in this question? ठीक है. Next question again on the confirmation JEE Main 2022. Whatever I'm saying is asked every year. Each and every point is very important. In the following structures, which one is having staggered conformation with maximum dihedral angle? Nobody should answer this question wrong. Nobody should answer this question wrong. What is the answer to this question? I'm again back to looking at the chat box. Which has the maximum dihedral angle? Which one has the maximum dihedral angle? B. Very good. सबसे Vikram is the highest in line. Then shoot out B. Yeah, I want lots of B's in the chat box. Lots of B's. A. Why are you asking A, bacha? A में the dihedral angle in between these CH3 is just bacha 60 degree. है ना? Only 60 degree. But here the dihedral angle in B option is 180 degree. So this has the maximum dihedral angle, na? So correct option is B. है ना? Maximum dihedral means what is the angle between the two methyl groups? Abhi I have explained you so many times. Correct? So that is how you understand. Next question, next electronic effects, very, very important. So many properties are asked. Acidic nature, basic nature, which one will show the most electrophilic reactions, which one will show the most nucleophilic reactions, correct? All these things are asked every year, very important electronic effects. Now let us look at the first electronic effect, which is the inductive effect. This is a permanent effect. All these definitions are very important. These words, this is a permanent effect, first word. Second, what happens in this? In this sigma electrons. Remember, no pi electrons are here. Only sigma. Sigma electron pair and not a complete transfer. In this, what happens, bacha? only a shift of electron pair happens. Complete transfer doesn't happen. ठीक है? It's a, like for example, if here fluorine is present. Fluorine is what? A most electronegative element. So what fluorine does, because it is so electronegative, it attracts electrons towards itself, but it do not transfers, it do not take the entire electron, it just attracts. सिर्फ ऐसे खुश है. For example, flirting करके लोग खुश रहते हैं ना, they don't want to get in a relationship. Flirting करके खुश. Same चीज इसमें है. Like the same thing is here. Like it just flirts with the electrons, it do not take it home, does not take it home. Okay, so here it just, and next is, it is observed due to the difference in the electronegative values, correct? Because for example, fluorine will be attached to some carbon atom. Carbon is less electronegative, fluorine is more electronegative, so therefore fluorine will attract electrons towards itself, correct? Inductive effect, there are two kinds of inductive effect. One is minus I, second one is plus I. What happens in minus I? Minus I actually decreases the electron density. Minus I means what? It takes away the electrons. ठीक है? For example, fluorine is more electronegative, it will take electron towards itself. Plus I means what? It donates electron. Plus I means it gives electrons. ठीक है? Now let us look at the order of the plus I series. Very, very important series. Very, very important. So the highest plus I means which will donate the electron maximum. Maximum donation happens in CH2, then NH. So what is the criteria? Either it should have a negative charge, or either it should have what? Either it should have lone pair of electrons. They will show what? They will donate the electrons because they are electron rich. ठीक है? उसके बाद ऑक्सीजन, उसके बाद CO माइनस, tertiary alkyl, secondary alkyl, primary alkyl, SiH3, Ct. You can skip these things. These things are not important. Then come back to CD3, CH3. Then T is what, bacha? T is a isotope of hydrogen. Tritium, deuterium, and hydrogen. Correct? So these are all isotopes of hydrogen. Everybody got it? This is the order. For example, CH2 will donate the most electrons, then nitrogen, then oxygen. And why is that order followed? Can anybody answer me that question? Why is carbon able to donate maximum electrons? Why it happens? Because bacha, can you, I will write down the electronegativity order. Electronegativity order of carbon, nitrogen and your oxygen. In between carbon, nitrogen and oxygen, which one is the most electronegative element? Most electronegative is oxygen, then your nitrogen, and then your carbon, correct? So this is the electronegativity trend. Electronegativity means what? It attracts. Electronegativity means it attracts electrons to itself very, very much. It does not want to lose electrons because I am very electronegative. I will keep my electrons to myself. I will not donate. Correct? So the least electronegative element is carbon, because carbon is not that electronegative. It is not attached to its electron. I am carbon. I am not attached to my electron. You can take it. So I can donate my electrons easily. Then nitrogen donates. Then your oxygen, because the oxygen is more electronegative. I do not want to donate my electrons even though I have many electrons. Even though oxygen has the most electrons, but still oxygen is higher electronegative. So I do not want to share electrons or donate my electrons. So therefore this order is followed. Everybody got this concept? This basic thing which I have taught you will be used in so many examples. Always remember, chemistry is based on basic things, and your JEE exam, especially recently from 2020, what has happened, a very drastic shift has happened where these basic things are asked in your questions. Basic things like what? Whatever these basic things I'm teaching you in class now, I'm not wasting my energy for no reason, because you will be able to solve a lot of questions based on this basic thing. Because I am carbon, I am less electronegative, so I will easily give away my electrons. Because I am oxygen, I am most electronegative, I will not give away my electrons easily. I will make you solve lot of questions using this basic concept. Okay? Everybody understood this concept or not? Everybody understood? Next is minus I series. What is minus I series means बच्चा? Minus I series means कि it will accept the electrons. ठीक है? Plus I means donation, minus I means accepting the electrons. So the most acceptance happens in the most electronegative element, because most electronegative will accept the electrons most. So NF3 will be the most, then NR3, then NH3, then NO2, then CN, then your aldehyde, then your acids, then your fluorine, chlorine, bromine, iodine, then your OH, OR, then your triple bond. Triple bond means what? Your alkynes, then your phenyl ring, then your strain ring, then your hydrogen. So this is the order. Very, very important order, and it is based on the same concept which I have told you right now. If I am more electronegative, for example, fluorine is more electronegative, therefore it will accept electrons more better way, right? So fluorine, then chlorine is less electronegative, then less, then oxygen is even lesser electronegative. Correct? So this is how you go. Now inductive effect. Why are we studying this effect? Because you will be able to solve a lot of questions of acidity and basicity order. For example, acid is what? Acid is your COOH group. Correct? This is your acidic group. Now why is anything acidic? It is acidic because it can give away what? It can give away its H plus ion. Correct? It will give away its H plus ion and become what? It will become COO minus anion. Correct? So now the acidity order will actually is based on what? How easily I can donate my proton. My proton is H plus. So carboxylic acid means what? How easily the carboxylic acid can donate its proton. It will depend on what? It will depend on the stability of COO minus ion. COO minus ion stability, it will depend upon. What does that mean? It means CO minus is electron rich. It has a negative charge. To make it stable, I need to do what? To make the negative charge stable, I need to accept the electrons. Correct? I need to accept. So what will I do? I will attach some electron withdrawing group. Means what? Electron withdrawing means it will take electrons towards itself. Some electron withdrawing group, which means what? Electron withdrawing groups were what, bacha? Were your minus I groups. Correct? They were taking away the electrons. So the more minus I the group, more stable will be the acid. Everybody got this point? To make the COO minus ion stable, I need to take away the negative charge, right? Because neutral atoms are the most stable. Nobody will want to live in a negative state or a positive state. Everybody wants to live in a neutral Zen state. Okay? So I have to make this negative charge neutral. To do that, I need to take away the electrons. Take away, who takes away? Minus I groups. So minus I groups increases, acidity increases. Correct? Everybody got this? Everybody got this concept? Next, we're going to do some questions based on this acidity order. See, look at this question. JEE Mains 2023. Easy peasy concept question. Who can answer this? The descending order of acidity for the following carboxylic acid is. You have to answer the descending order of acidity for the following carboxylic acid. Who can answer this question? Who can answer this question? I am looking at the chat box again. I am looking at the chat box. So whenever I start looking at the chat box now, people go away. Why? Why are you not answering the questions? But do not be afraid. Answer these questions. Okay? See. Okay, let us look. Very, very good. First was Hemant, very. ठीक है? Thank you. C answer Sanjay. C Hemant. C. Okay, shootout. JEE C. Very good. So first one was Hemant. Very, very good. So what is happening, bacha? Ki I just told you acidity order means what? Acidity order will depend on the stability of the COO minus ion. ठीक है? CO minus ion stability it will depend upon. So how many electron withdrawing groups I'm going to attach? I'm going to attach the minus I group, right? It will depend on the kind of the minus I group I have attached. Now let us look at the B option. B option is what? It has, bacha, look at it. It has 3 fluorines. Fluorine is what? A very good electron withdrawing group. It will withdraw the electron. So this will be the most acidic. Next will be the D option, which is your, again there's 1 fluorine here. So again it will be the next better acid. Next will be the C option, which is your chlorine. Because how the minus I trend follows, bacha? Minus I trend follows like this. Because fluorine is most electronegative, it will withdraw most of the electrons. Then it will be chlorine, then it will be bromine, and then it will be iodine. Correct? So this trend will be followed. So because the highest fluorine atoms are attached in B, so B will be the most acidic. Then 1 fluorine atom is attached in D, so D will be usse less acidic. Then will be your C option, which has chlorine. So it will be C. Then it will be your E, because it has bromine attached. And A, it is a simple acetic acid. It does not have a electron withdrawing group. CH3 is what? CH3 shows plus I effect. Correct? So this is the least acidic compound. Acetic acid is not that acidic. Correct? Let's move on to the next question. Arrange the following in increasing order of reactivity towards nitration. Nitration means what? For nitration, what kind of atom do I have to use for nitration? This is the NO2 plus. NO2 plus electrophile is used. NO2 plus electrophile. ठीक है? NO2 plus electrophile is actually used to cause nitration. अब this has a plus charge. For plus charge, plus charge is attracted to what? Plus charge is attracted to a negative charge, correct? So for the maximum nitration to happen, the ring should be electron rich, correct? So the more electron rich the ring is, more nitration will happen. Did you get this concept? For nitration, this is your electrophile. ठीक है? NO2 plus is used. So plus will be attracted to a negative charge. So the ring should be electron rich. So the more electron rich the ring is, more will be what? More will be your nitration. ठीक है? So if let's see the answer to this. The answer to this is actually this. ठीक है? See, look at here this benzene ring. This product is called bacha mesitylene. This is called mesitylene. This is called xylene. Okay, all these common names you must know, because see, this is a JEE Main 2022 question and common names are every day asked. So whatever common names are given in your NCERT, you must be very familiar with it, because can you see, only common names are written. Otherwise, this concept is very easy. Mesitylene means what? 3 CH3 groups. So 3 CH3 groups will actually, CH3 groups are plus Psi groups. So it will donate the electrons to the ring and their benzene ring will become electron rich. If it will become electron rich, therefore NO2 plus iron will what do? NO2 plus iron will be able to attack the ring very, very much. Correct? Next is your xylene. Xylene, in xylene what happens? There are just 2 plus I groups. 2 plus I groups means what? 2 groups are actually increasing the electron density. Similarly, this is your benzene ring and now bromine. Bacha, bromine is what? Bromine has a minus I effect. It will take away the electrons. But I want the electron rich ring, correct? And then the NO2 will take even more electrons. NO2 is a better minus I group. So how am I able to distinguish between these two? Based on this table. Based on this table. Can you see? NO2 is the most minus I group than your Br. Right? Br is here in this series and NO2 is here. It means what? NO2 is one of the best electron withdrawing groups than your bromine. Correct? Anybody has any doubt in this order? For NO2 plus electrophile to attack what do I need? I need a electron rich ring, है ना? Because this is a positive charge, so it will attract a negative charge. Negative charge means what? Electron rich ring. So electron rich means I need to follow this order. Whatever plus I groups, maximum plus I groups are attached, that will be your maximum that ring will show maximum nitration. Anybody has any doubt in it? Anybody has any doubt? Next we are back to the very amazing resonance effect. We are back to resonance effect. In resonance effect, bacha, what happens? Resonance means what? Whenever a true structure of a molecule, just leave reading this thing. It means, I will just show you the diagram. For example, a resonance structure is always a mixture of two structures. Let us look at what is resonance first. Okay, then I will make you understand. For example, there are types of conjugations happening in resonance. Okay? First is pi sigma vacant orbital. It means what? Look at this compound. Look at this compound. Forget whatever it is written. Look at this compound. This is what? CH2 double bond CH, and here it is a positive charge. It means it is a carbocation. Carbocation means what, bacha? Carbocation means its p orbital is, bacha, what? It is a vacant. It has a vacant p orbital. Correct? So what can happen now? So here there is another very important thing you have to focus on. This is a double bond here. Then there is a sigma bond. Correct? There is a double bond which is a pi bond. Then there is a sigma bond, and then there is a vacant p orbital. Correct? So you have to follow this order. This is called in conjugation. Conjugation means what? Whenever there is any two things separated by one single bond. Any two things separated by one single bond. For example, here the double bond and the positive charge is separated by one single bond. Therefore, these two, the pi bond and the p orbital, are in conjugation. Okay? So always look for this kind, a double bond, then a single bond, then a positive charge. Okay? Only then this kind of resonance will happen. So what is happening in this resonance now? Now what is happening in what is happening in this resonance? This electron, this pi electron actually moves here. This pi electron moves here, and what happens then? Then this positive charge actually moves to this carbon. This movement of electrons, what is happening? Nothing, only electrons are moving. So this movement of electrons is called resonance. Okay? This is called resonance. So can you see, when I moved these electrons here and the positive charge here, there's another structure created. So now this structure is actually can resonate and form this structure. Okay? But the actual structure, so now you will ask him, ma'am, then what is the actual real structure between these two? Then none of them. Neither this is the real structure, neither this is the real structure, but the actual structure is somewhere in the middle, where both the bonds have a partial double bond character. Can you see? Where both the bonds have partial double bond character. This is called, bacha, what? This is called, where both the bonds have partial double bond character. This is the actual structure. Now what I'm doing here, next thing which you should notice, ma'am, you are making a single bond into an actual double bond, and also you are converting a double bond into an actual single bond. Can you see? I'm making this single bond double here, right? But also I'm converting this double bond into single bond here. Can you see? So what is meant by that? What is meant by that? It means that the bond length of both these bonds here, which have a partial double bond character, the bond length is in between a single bond and a double bond. Correct? The bond length is in between a single bond and double bond. It is neither fully single, neither fully double bond. Okay, everybody got this point? Everybody got this point? Next Now let's see another kind of conjugation. We are seeing this one, pi sigma vacant orbital, which means there will be a double bond, then a single bond, then a positive charge. Okay? It can happen in case of benzene also. Can you see benzene? Benzene here, it is a double bond, then a single bond, and then a positive charge. Everybody can see that? Now I can move the double bond like this, and the positive charge will actually resonate in the ring at the ortho and the para position. Everybody can see that? See? So this movement of positive charge. So whenever there is resonance, what is the, ma'am, why are you teaching us this? Because bacha, whenever a compound can show resonance, more the resonating structures. Can you see it has 1, 2, 3, 4, 5 resonating structures. So more the number of resonating structures, more will be the stability of the compound. Always remember, this has only 2 resonating structures, but your phenyl, this is what? This is your benzyl, sorry, not phenyl. This carbocation is called benzyl carbocation, has 6 resonating structures. So this is the most stable kind of carbocation. Okay? Next, I am back to this. This is cyclopropyl carbocation. Okay? This also carbocation shows resonance like this. Okay? So again, I can show resonance like this, where the double bond moves here and the positive charge moves here. Why does this show resonance? Because can you see a double bond is present, and then a single bond, and then a positive charge. All the conditions for the pi sigma vacant p orbital are satisfied. Therefore, this compound also shows resonance. Everybody understood? Now we are back to another kind of resonance, where there is a pi bond, there is a sigma bond, and then there is a free radical. In last time we learned a pi bond, a sigma bond, and the positive charge. Here a pi bond, a sigma bond, and a free radical. Okay, similar kind of resonance happen here. The electrons move here, the double bond moves here, and the free radical moves here. Again, the actual structure is somewhere is the hybrid of these structures. The real structure is actually a hybrid of these two structures, and this kind of bond is formed. Everybody understood? Okay. Now let's move to the next example of the same. Here again in benzyl carbocation, can you see a double bond, a single bond, and a free radical? Okay. And again these three will show what? Resonance. It will form again 6 resonating structures. Therefore, benzyl carbocation is again a stable carbocation. Understood? Next, pi sigma negative charge. See, pi sigma negative charge also shows resonance. Here what happens? This negative charge will move here and it will form a double bond, and this double bond electrons will move here. So this is how electrons move in this, and again a hybrid is formed. A hybrid structure is actually the real structure of this kind of conjugation. So are you understanding conjugation? In resonance, what is happening? Nothing. There is movement of electrons, and how? Either from pi sigma positive charge. Okay? Next was pi sigma free radical. Next was pi sigma negative charge. Can you see? So we have done all kinds of, and now next kind of resonance is pi sigma lone pair. Okay. Now look at this lone pair. Again, I can move this lone pair here. Okay. And if this lone pair will move here, the pi electrons will actually move here, and it will form a resonating structure like this. CH2, यहाँ पे there will be negative charge. Here it will be CH double bond OH. Like this it will be formed. Here it will be positive charge. Okay? So this is the resonating structure of this. Similarly, you can draw for this and as well as this. Okay? Next, stability of resonating structure. So now we have discussed the various kinds of resonance that can happen. What was the basic condition? There should be a pi bond, there should be a sigma bond and a positive charge. Pi bond, sigma bond, free radical. Pi bond, sigma bond, negative charge. Pi bond, sigma bond, lone pair. That is it. Only if this condition is present, it will show resonance. Now, how you will see the trend, which is more stable and which is less stable. So, number first thing, can you see? Can you see? the compound which has the maximum number of covalent bonds, remember, which has the maximum number of covalent bonds is considered to be more contributing than others. It means it is more stable structure. Okay? For example, can you look here? This compound has 1, 2, 3, 4, 5. 5 covalent bonds. Okay? Here how many are there? 1, 2, 3, 4. Here only 4 covalent bonds are there. Can you count the covalent bonds? Therefore, this structure is more contributing structure. This structure is more contributing because it has more covalent bonds. So first stability, how you will figure out the first stability? By counting the number of covalent bonds. Okay. Next pointer to consider is that the positive charge. Okay. And next is कि if both of them has same number of what बच्चा? Same number of covalent bonds, then how you will find out which is more stable? Then you will actually count which has this octet complete. ठीक है? For example, in this structure, which one has the octet complete? Can you tell me? Which of them has the octet complete? It will be more stable. ठीक है? Next thing, let us come here. Now the stability, now let us look at the stability of A and stability of B. So what is the difference between these two, bacha? Here the negative charge is on carbon, but here the negative charge is on oxygen. Correct? Now if the negative charge is on the more electronegative atom here, so the negative charge on more electronegative atom is oxygen. So therefore B is more stable than A. So negative charge is more stable on a more electronegative element, but carbon is less electronegative. So this charge will not be stable. Therefore between these two structures, B is the more stable structure. Right? Now let us look at this example. Who can tell me the actual stability order after considering all the points that we have mentioned? Okay, I will teach you another important point. What is the order of stability of these resonating structures? Who can tell me? 2, 3, 1. Somebody has answered Uchuk Puchuk. Okay, what is that name? Uchuk Puchuk. Uchuk Puchuk has answered 2, 3, 1. 2, 3, 1. 2, 3, 1. Okay. Now let me begin. The first rule was count the number of covalent bonds. Let us count number of covalent bonds in each compound. This compound has 4 covalent bonds. 1, 2, 3, 4. Correct? This one again has 4 covalent bonds. How many this has? This has just 1, 2, 3 covalent bonds. Okay? So now these two have bacha same number of covalent bonds. Okay? So now I know that the number one stable compound will be between either 1 or either 2. Now which one do you think is more stable between these two? Okay? So now can you see the negative charge in the first compound? In the first compound, can you see that there is what bacha? A negative charge on the nitrogen and a positive charge on the nitrogen. Correct? But in the second compound, there is a negative charge on the CH2 and a positive charge on the nitrogen. Correct? So which one will be more stable between these two? So so here we were talking about, so here can you see the negative charge is stabilized actually on the nitrogen, because nitrogen is bacha what? More electronegative element. Hai ki nahi? Nitrogen is more electronegative. So here the negative charge will be more stable on nitrogen. So number 1 will be more stable than your number 2. Why? Because here the negative charge is gained by carbon. Carbon is less electronegative. It cannot take any more negative charge. Nitrogen can take because it is higher electronegative. So therefore nitrogen wali cheese is more stable than your second, and then comes your number 3. Okay? This is the order 1, 2, 3. Anybody has any doubt in it? Everybody understood this, bacha? Everybody understood this? let's move on to the next question. The next question is this. Tell me the stability order of these resonating structures. Which will be the most stable structure? Now the number first thing which we are actually looking at is count the number of covalent bonds. More the number of covalent bonds, more stable will be the structure. Number second is, look at where the negative charge is present. Negative charge should be focused on more electronegative element, that will be more stable. And also number third point to consider is that the charge separation should be minimum. Correct? The positive and negative charge should be together. The more they are together, more stable will be the compound. The more far apart, less stable will be the compound. Okay? These three things you have to consider. Write down in your copy right now. Everybody understood? 3, 1, 2, 1, 2, 3. I am getting mixed answers. 1, 3, 2. Everybody is giving mixed answers. Now let us look at all these compounds. This has how many covalent bonds? 1, 2, 3, 4, 5, 6, 7, 8. I can see 8 covalent bonds here. In the second, 1, 2, 3, 4, 5, 6, 7. 7 covalent bonds. Here, 1, 2, 3, 4, 5, 6, 7, 8. 8 covalent bonds here. So now I have to decide between 1 and 3 first. Now look at the first structure. Look at the third structure. The third structure actually has separation of charges. Can everybody see? Third structure actually has separation of charges. 1 second. Yes. Third structure actually has separation of charges. Therefore, it is less stable. I am telling you, the charge separation should not be there. So, first will be more stable, then your third, and then your second. This is the order. Okay. First of all, charge separation should not be there. And if it exists, then the charges should be together. Positive and negative should not be far apart. Everybody got this point? Everybody got this point? This is the order. 1, 3, 2. 1, 3, 2. Everybody understood this? Yes, yes, correct, correct. Everybody gave the correct answer. Now let us look at the stability of this. Okay, now here it is explaining resonating structure in which unlike charges are closer is more contributing than the structures. Okay, so the positive and negative charge should be closer. That will be the more stable structure, which I explained to you right now. For example, look at this phenol molecule. Now the phenol molecule has all of these resonating structures. How have I made it? I moved this electron here and this pi bond here. Correct? This is how the movement happens. And here comes a negative charge. Negative charge then goes from ortho, para, ortho direction, and these are 1, 2, 3, 4, 5 resonating structures formed. Now tell me the stability order of which is the most stable structure, which is the least stable structure. Okay, so the most stable, I told you, most stable is where there is no charge separation, where there is no positive negative will be the most stable. So I can see that in the first structure and in the fifth structure there is no positive negative, there is no charge separation, there is just a normal neutral compound. Correct? So first and fifth are equally stable and most stable. Next come, look for the where the charge separation is least. Can you see in the second and even in the fourth? In the second and fourth, here is the negative charge, here is the positive charge. In the fourth, here is the negative charge and here is the positive charge. So the charge separation is least in second and fourth. Okay? So then second and fourth will be equally stable but less stable than first and fifth. Now the least stable will be the third compound, because look, the positive charge is here and the negative charge is here, which is too far apart. So when the positive and negative are too far apart, then it is the least stable compound. Can you tell me? Now you know how to look at these things. Okay. Now let's move on to the next. Resonating structures in which like charges, we have already discussed this. We have already discussed all the things. The three things you need to know while finding out the stability of resonating structures. I told you all the three things. Number first, count covalent bonds. Number second was what? See, the negative charge should be on the more electronegative element. Number three, the charge separation, first of all, should not be there. And if it is there, if positive negative happens, then the positive negative should be close. More closer the positive negative, higher will be the stability. These 3 points finish resonance. Now come to stability of resonating structures in cross and extended conjugation. Okay, cross conjugation means what? Whenever this kind of conjugation happens, can you see that there is a conjugation happening? Conjugation, what was the meaning of conjugation? I told you, when the double bonds are separated by single bond, one single bond, correct? When two double bonds are separated by one single bond is called a conjugated structure. See, two double bonds are separated by one single bond. Two double bonds are separated by one single bond, correct? So these are conjugated structures, which is correct. But this kind of conjugation is called cross, where can you see the another methyl group is actually like a substituent to this main chain, correct? This is how we calculate the main chain. If this is the main chain, the next methyl group is actually like a branch, correct? So this kind of conjugation is called cross. Extended means when all the double bonds are in one straight chain. Can you see, this is a straight chain hydrocarbon and these all bonds are conjugated, separated by one single bond. This is called what? This is called extended conjugation. Okay, and which conjugation is actually better? Then extended conjugation is more stable than your cross conjugation. Always remember this. Okay, this is more stable than this. Okay, next. Now let's practice these questions. Answer me. For the first, this is A and this is B. Which is more stable? This is A and this is B for second. Which is more stable? Tell me. I'm looking at the chat box again. I am looking at the chat box again. I am looking at the chat box, bacha. Tell me. Tell me. What do you mean by one, bacha? Is A stable or is B stable? Tell me this. A is more stable than B or A is less stable than B? Answer that. Write in that format. Write in that format. What do you mean by one, bacha? A, B, B, A लिख रहे हैं everybody. ठीक है. So bacha, here, can you look here and here? So what is happening in this NH2? This electron pair can move here, right? Then this bond pair can move here. Then this electron can again move here. So can you see there are so many resonating structures possible for this compound, right? Now let's move on to this compound. This is N. Now here what can happen? Either these electron can move here and then this double bond will move here, right? So this is the first probability, okay? And the second probability is what? Otherwise the electron move here and the double bond electrons move here. So this is the second probability, right? But here can you see the extended conjugation is happening, right? The electrons are moving like a wave and it is very extended, but here the conjugation is separated. Either the electrons will move to the right side or to the left side to just one place, correct? So this is actually less stable. So more stable conjugating structure is this one, correct? Understood? Because this has extended conjugation. I just taught you extended conjugation is more stable conjugation. Now answer the second part. What is the answer to the second part? A is more than B. Somebody is writing to the second part. To the second part. To the second part, let us look at the second part. Now the second part again, can you see? This shape looks like a cross conjugation shape. Can you see? This is like a cross conjugation. You can just identify the shape. बच्चा ऐसा ही होता है ना, cross conjugation. And here, this one is a extended conjugation. This has a lone pairs here, correct? So this double bond can go here, and then this can go here, and then this can go here. So it has like a extended conjugation. This has extended conjugation. Therefore, this is more stable than that one because that is cross. This is extended. Everybody got this point? Everybody got this point? Okay, this is the answer. Now answer this question. Stability order, you have 1, 2, 3, 4, 5, 6 compounds. A, B, C, D, E, F. What will be the order of stability? I am giving you 1 minute. That's it. That's it. You get 1 minute. Answer this question. Tab tak I will drink some water. I will drink some water till then. Beta, you have to compare stability of each and everything. A, B, C, D, E, F together. Which will be the most stable compound? Okay, I will explain it to you. Let's not waste any more time. Now here what is happening? I told you the first thing is to calculate the number of covalent bonds. But I can see everywhere the number of covalent bonds is same. Okay? The next thing which I have to calculate is what, bacha? That the negative charge should be on the more electronegative element. Can you see? Here the negative charge is on carbon. Carbon, here the negative charge is on bacha oxygen. Can you see? Here the negative charge is on oxygen. Therefore, this will be most stable. D will be more stable. Now, look at E. E has again negative charge on oxygen. Correct? So, now the stability will be E. Correct? Now, what do I have to look for? Now, what will be the stability order? D, E. Then what will I look at the things? D, E, B, C, A, F. Very, very good. Very, very good. Okay, and now let's look at these chain compounds. Always remember, bacha, if you have to compare the stability between a ring compound and a chain compound, and you are considering, bacha, what? And you are, can you see? Okay, now I'm going to answer. I've received so many responses, but none of them are right. Now you may ask, ma'am, why is D more stable than E? Because E has, ma'am, so many resonating structures, correct? This one will have so many resonating structures, na? Either pay this can move here, the negative charge will come here, then here, and then here, right? So this will all be the resonating structure of this compound. So this has actually so many resonating structures, but still, this is what, bacha, less stable than this chotu sa compound. Why is that the case? That is the case because here, can you see again, the negative charge is actually migrating to carbon. Here what all is present? Here carbon is present, carbon. So negative charge is coming to carbon, which is what? Less electronegative. Therefore, this is actually less stable because here the negative charge is transferring where? The negative charge comes here, and then again this double bond goes here and becomes negative. So the negative charge in D stays on just and just oxygen. Therefore, D is most stable than your E compound because here the negative charge is on oxygen. Now let's come back again to A, B, C. A, B, C, correct? In between A, B, C and F, these are left. Now in between these three things, now if I move the negative charge, if I move, here the negative charge comes on oxygen, correct? This will come here, the negative charge will come in oxygen. So therefore B will be more stable. Then here the negative charge, if I move, then it will come on nitrogen, which is lesser electronegative than oxygen, but more electronegative than carbon. So therefore then it will be C. Now here the negative charge comes on this carbon, correct? Now in between A and F, which one will be more stable? Which one will be more stable? Because in A also the negative charge is coming on carbon, and in F also, if I am rotating the negative charge, resonating the negative charge, it again comes on various positions of carbon only, है ना? But here the resonating structures are more in number, correct, in the benzene ring. So therefore F will be more stable than your this compound. B compound, which one was left? A compound. Okay? So this is actually the order. Does everybody understand this? Does everybody understand this? Okay? Everybody understood this, bacha? Can I move forward? Okay? So the negative charge should remain on more electronegative oxygen, more electronegative element, first point. Okay? Either because negative, even though this benzene ring has more resonating structures, but the negative charge is actually transferring to carbon, which is lesser electronegative. Therefore, this is lesser stable structure than this one. Okay? You got all the points? All the points are in your mind? Perfect. Perfect. Let's move forward. Let's move forward. Okay. Now there comes a very interesting effect called the steric inhibition in resonance. Now I have shown you resonance effect of various types, but sometimes even the resonance is inhibited, means what? It is decreased or it doesn't happen. Why? Due to steric reason. For example, if in this compound what I attach like a alkyl group here. Okay, if in this compound I attach a alkyl group here, what it is doing? It is causing a very much steric hindrance effect to it, right? So what it will do, it will not let resonance happen due to this alkyl effect. This is called steric inhibition. That's it. Okay? So because the resonance is decreased in this case, right? The resonance is decreased in this case. And as the resonance is decreased, because due to resonance, what will happen? This bond will form in the first compound. This one will have, bacha, a negative, partial negative bond character, but this one will not have a partial double bond character, correct? This one will have a partial double bond, this one will not have a partial double bond character, right? So therefore the bond length of Cn, the bond length of Cn here will be lesser, correct? Because this has a partial double bond character. This bond, Cn bond, this Cn bond will be smaller and this Cn bond will be bigger, correct? Because this has a partial double bond character, because here the resonance is happening. Here the resonance is happening, here it is not happening, correct? Now the bond strength in Cn. Bond strength means same order. If the bond is smaller, it will be stronger bond, correct? Just like me, I am very small and very strong. Next we will compare, let's practice. Compare the bond lengths. Now, can you tell me the order of bond lengths between 1, 2, 3, 4? Which will has the highest bond length? Which will have the smallest bond length? Tell me the order. I will give you 40 seconds. Answer me. 40 seconds, answer me. Yes, bacha, all of this will be uploaded on Telegram. All the notes I will provide to you on Telegram. Join the Telegram link today after the session is ended. By the end of the day, the notes will be uploaded for sure. For sure. Okay? Beta, level of questions for organic is increasing day by day. That's why I'm teaching you everything from basics, correct? That's why I'm teaching you every little nook and crook of thing. 2, 4, 3, 1, 3, 4, 2, 1. I'm getting mixed answers. 4, 3, 2, 1. Okay, I'm getting mixed answers to this. Let us look at the bond length order. Bond length order. So I know this is a single bond length. And I know that single bond length is the most longest bond length. So first will be the highest bond length, correct? Because this is single. Now next comes, this is a proper double bond, correct? So this one will be the smallest. So second I know, second will be the smallest. Now I have to compare between 3 and 4. So between 3 and 4, which one will have which one will have a longer bond length? ठीक है, which one will have a longer bond length बच्चा? 3. Look at the position of 3 बच्चा. Now this has much more resonance. This fourth structure has the resonating structure goes here, then this goes here, then this goes here. So it has like a lot of resonating structures. Okay? So the this one will be even shorter bond length. Here will come 4th number and here it will come 3rd number. Correct? So the 3rd number has only one resonating structures. Correct? This will move here and this will move here. That's it. So this has lesser resonating structures. Therefore the bond length will be a little longer. But here the resonating structures are so much more. So the bond length will be even shorter, and this is a proper double bond. This one will get a partial double bond character. Partial double bond character. Correct? So this one will be what, bacha? Partial double bond character. Correct? Correct? So you understood the order 1, 3, 4, 2. This is the correct order. If anybody gave this answer, you are absolutely right. Okay? Now, which one among the following is not correct? Which one of the following resonating structure is not correct? JEE 2021 question. Who can answer this? Can you clearly see everything on the board? I will write. Can you clearly see everything? Let me check. I think it is extremely clear. Yes, it is extremely clear. Answer to me. What is the answer to this question? Okay. First, very, very good. Xenomosh 202 has already answered it. And it is a very, very correct answer. Correct. So, bacha, what is happening in first? Can you see? There are 2 positive charges together. Can you see? 2 positive charges or 2 negative charges can never be together because they will repel each other so badly that this structure will be least stable structure. So this was the easiest question of all using your basic chemistry. You don't have to apply any mind tricks, anything. Any mind tricks, whatever teachers, YouTube teachers give you is not important. Now JEE has completely changed the way to look at organic, especially organic chemistry. But it is just these basic things. 2 positive charges together. Least stable, positive charges repel. 2 negative charges together repel. Least stable structure. Correct? Sorry. This is the least stable structure. Now, which of the following compounds does not exhibit resonance? Resonance. Which doesn't exhibit resonance? Tell me. What is the answer to this? Correct. So the funda to actually learn organic chemistry is the basics. I'm telling you, time and again, I am seeing the question papers of JEE Mains, and no funda, no tricks will help you till you are very deep into the basics. Basics, why? That is the only thing we are learning here. If your basic is strong, your hold on organic will be mind-blowing. Even if we miss the name reactions, because name reactions, you can just do it by yourself. These basic things, nobody will teach you. I can give you a lecture on name reactions. What will happen with that? Nothing. You will learn nothing from me, nata. But from these basic things, you are learning so much. Negative charge, positive charge, which will actually gain electrons, give electrons. These are the important things. Okay. D answer, D. Very, very good. And how does that happen? See, in A, this resonance is possible. In B, the benzylic resonance is possible. In C, again, this kind of amide resonance is possible. In D, there is nothing. There is just a double bond and there is no positive charge, no negative charge, no lone pair, no free radical. These things are important for me to perform resonance. Here, a lone pair is present. Correct? Here, double bond is present. Here, again, a lone pair is present. Correct? Next question, JEE Main 2021. Among the given species, the resonance stabilized carbocations are. See, all these things which I have taught you are asked in exam. I'm not teaching you faltu things. I'm teaching you very important things. Answer me. Which among the given species, the resonance stabilized species carbocations are? Which carbocation is resonance stabilized? So you know what is the condition? There should be a pi bond, then a sigma bond, then a positive charge. Only then it will show a resonating structure. This is the basic condition which I've taught you 100 times right now. Correct? So people are answering C and D. C and D. Correct? C and D. C, D, D. I'm getting so many responses. Nobody has answered. Okay, one person has answered. Correct answer is actually C. How? Look at all the structures. Look at all the structures. The first structure is CH2 positive. So there's a double bond. There's a double bond. Then a sigma bond. Then a positive charge. First condition for resonance. Yes, this carbocation is resonance stabilized. True. Next is this. Look at this. This is again a pi bond, and then there is a sigma bond, and then a positive charge. Correct. This is again resonance stabilized. Correct. This is a basic condition. There should be a pi, sigma, positive. Correct. So this condition is satisfied here. Now look at here. Now here there is a pi bond, a sigma, and then again a sigma. No. There should be just one sigma. The positive and the pi bond should have just one sigma bond. Then only they are in conjugated manner. Correct? Then only they are conjugated. This is not. So this will not show carbocation resonance. Now look at this structure. This structure has a pi bond and a positive charge on the same thing. There is no sigma bond in between them. Therefore, this will again not show carbocation resonance. See, the basic thing I taught you in the resonance, on that basic thing, this question is asked. So all the things I'm teaching are extremely important. All the notes that you will get in the telegram are extremely important. If you just revise them, I'm telling you, if you have done 0 in chemistry right now, still you can score amazing marks if you just know these things. I am pretty sure. Okay? Next. Our next effect is mesomeric effect. So we have already learned resonance. Now resonance effect is used in another thing. It is called mesomeric effect. Okay? In mesomeric effect, bacha, what happens when the same thing, that the lone pair of electrons, this kind of resonance happens. Okay? So whenever this kind of resonance happens in organic compounds, it is called a mesomeric effect. Whether you call it resonance, whether you call it mesomeric effect, it's one and the same thing. Okay? So we have learned till now how many things? We have learned inductive effect, which was a permanent effect, and there were two types of inductive effect, plus I and minus I. And I taught you the order, the series of that, correct? Plus I, minus I. And we use the plus I, minus I to look at the acidity trends. You know, very important acidity trends. Now we are reading about mesomeric effect, which is like your double bond, your electrons will provide double bond character to your single bond. But it means it is a kind of resonance only, correct? So for resonance, what is the condition? There should be presence of a lone pair of electrons. So these are the compounds which shows a mesomeric effect. So therefore, for showing mesomeric effect, the condition is the element should have lone pair. See, OH has lone pair, OR, NH2, NHR, NR2, SH. Everything mentioned here has lone pair. So it will give its lone pair to the compounds and the resonance will happen. And when it gives a lone pair to the compound and resonance happens, that effect is called mesomeric effect. Okay? It is not different than resonance. It just has a different name. Correct? Now, plus M effect. Plus M effect means what? For example, which donate the electron to the compound. Which donates the electron to the compound. For example, CH2 minus. Now the plus M effect order. Again, look. Here the order is what? CH2 donates more electron than NH than O minus. Why is that trend? I just told you. I told you a while back, because Oxygen is the most electronegative element. It do not want to give away its electron. It holds its electron very closely because it is a more electronegative element. Correct? It is most electronegative, so therefore it will not give away its electron easily. Nitrogen will give away a better way, and CH2, carbon, will give its electron in a much better way because carbon is what? Less electronegative, so it is not attached to its electron with give away. Okay, go take my electrons, okay? Because it is less electronegative. Next, NH and NH2. NH is a NH and this is NH2. Okay, so NH is a better electron donating group. Next, NR2, NHR, NH2. So this is all the orders. So can you see as the alkyl groups are increasing, can you see as the hydrogen increases, see lesser hydrogen, what happened? Yeah, okay, we're back. I'm really sorry about that. I'm really sorry. So as the hydrogen increases, the capability to give electron decreases. But as the alkyl groups, R means what? CH3 group. As the alkyl group increases, the capability to give electrons actually is increasing. Can everybody see? NR2, then NHR, then NH2, then NHCOR. CO means what? CO does what, bacha? Oxygen is electronegative element. So it has a tendency to withdraw electrons. So this is a electron withdrawing group. So as you are attaching electron withdrawing group to the NH atom, what you are doing? You are attaching, one second. Yes, you are attaching electron withdrawing group. So therefore this electron will move here and this electron will move here, and therefore this NH cannot give its electron easily now, right? Because these electrons are now participating in a resonance. Therefore this will not give its electrons easily. Now look at this, because now I have increased the COR group. So this is the least, this will show the least plus M effect. Plus M means what? It will donate the electrons for resonance, okay? Now same trend is followed for oxygen, then your NH2 and then your FCl-BRI. Now fluorine will give most of its electron, then chlorine and bromine and iodine, correct? Now let's move to the minus M effect. In plus M, what was happening? In plus M, this oxygen is giving its electron to the compound. Can you see? And this kind of resonance is happening. But in minus M, minus R effect, what is happening? It is taking away electrons. So these are electron withdrawing group. And these are electron donating groups. So for electron donating, can you see? Every group either has a lone pair or a negative charge. Only they can donate the electrons. Either I should have a lone pair or a negative charge, correct? But in electron withdrawing group, the major best thing to find out whether it is a donating, it takes away electrons, it is the presence of a multiple bond in the compound. For example, NO2 has a multiple bond. Okay, you don't have to remember which will give, which will take. It will take so much time. Just remember every compound which has a multiple bond in it. For example, NO2 or C triple bond and again has a multiple bond in it. So these are all your what? All your electron withdrawing groups. So it will take away electrons like this, but again causing a resonance, correct? This is a resonating structure, and these are all the groups which show your what? Which shows your resonance effect. Anybody has any doubt in it? Does anyone have any doubt in this? See, this has a multiple bond, this has a multiple bond, multiple bonds. So every structure which has a multiple bond, if it is attached to your compound, it will act as a electron withdrawing group. It will take the electron towards itself, okay? And if it has a lone pair or a negative charge, it will give away its electrons, okay? Now next minus M effect order is this. Most minus M, see, it is shown by NO2 group. It is the highest, it shows the highest minus M effect. Then your CN group, then your aldehyde ketone, then your ester, and then your amide group. Okay, remember this trend. Okay, because there will be so many questions based on acidity, basicity, that if you don't know this trend, like which actually gives the most electron, which is lesser than that, how will you judge the acidity? For example, I have attached to a benzene ring a NO2 group, and also to another benzene ring I have attached a CN group. Okay, now now the question is, which one is more acidic? So for that you need to know what? This order, that NO2 withdraws most electrons, right? I will attach a COH group here and a COH group here, correct? Now this has become an acid, correct? And this will attract less electrons, correct? And I've told you what is the condition for acidity. The condition for acidity is how easily the H plus is taken out, है ना? How easily the H plus is taken out, it is more acidic. And it depends on what? It depends on the stability of COO minus ions, correct? Depends on the stability of COO minus ions, है ना? Next, which of the following JEE Main 2020 question, which of the following has the shortest CCl bond? Who can answer this? Which has the shortest CCl bond? I am looking at the chat box again. I am looking at the chat box. Who will answer this question? I am looking at the chat box, bacha. B. B. Somebody is saying B. Very, very good. Very, very good, Akhilan. Akhilan, very, very good. Keshwani and then Ishwarsh. Nobody has given, then Akhilan only has given. Only 2 people have given best answer. Okay? Beta, shortest bond means what? When it will have a short bond, when it will have a partial double bond character. Correct? So only a partial double bond character. Where can you see? Here NO2 group is attached. Correct? NO2 group will do what? Will take away the electrons. Take away the electrons. This will move here. Right? And this electrons will move here. For example, this will happen. These electrons will move here. This electrons will move here. And these electrons will move here. Okay? So this kind of double bond, this bond will get a partial double bond character. So therefore this bond will be smaller. So the answer is B. Again, based on what? Your minus M effect, which is an electron withdrawing effect. Okay? Very, very good. Very, very good. Next, hyperconjugation, our very last effect, which we are going to study. Very, very last effect, and then acidity, basicity, and that is over. Over. Very basic chemistry is over. Okay? Hyperconjugation, again, this kind of effect is, again, a permanent effect. Okay? And what happens in this? Right next to a alkene. Can you see here? An alkene is present. So right next to the alkene, the alpha carbon. Alpha means right next to the alkene carbon. The first carbon is called the alpha carbon. The alpha carbon should have alpha hydrogens. Correct? Then that will show hyperconjugation. This is a kind of effect. You don't have to understand what happens in it because no questions can be made on that. You just have to know that the alpha carbon should have alpha hydrogen, and more the number of alpha hydrogen, more will be the hyperconjugative effect. Okay, let us see some example. For example, the electron order of electron release based on inductive effect. We have already studied inductive effect. In inductive effect, what happens? As the methyl group increases, what it does, it is a plus psi effect. It is an electron donating group. So it is actually increasing with what? It is increasing the electron density here, and here it has less electron density, lesser plus I effect, and this is about the plus I effect order. Correct? Now the electron donation density based on hyperconjugation. So I told you in hyperconjugation what matters is the number of alpha hydrogens. For example, here the alpha hydrogens is 3. Here the alpha hydrogen is just 2. Okay, so this is less, and here the alpha hydrogen is just 1, and here the alpha hydrogens is, this is the alpha carbon, not this. This is the alpha carbon, so here the alpha hydrogens are 0. Okay, so this will show the most hyperconjugative effect, and this will, like the tertiary thing, will not show the most hyperconjugative effect. So this is the, so the inductive and the hyperconjugation effect are reversed effects. Correct? Now let's see this. Now what happens, bacha, in now where do we see the hyperconjugative effect? In alkenes. Number first is alkenes. In alkenes, hyperconjugation is seen more. Hyperconjugation is weighed more than inductive effect. Okay? In acidic character of alkene, if I have to know the acidic character of alkene, then hyperconjugation weakens the alpha CH bond. It means what? That as the stability, as the hyperconjugation increases, acidity of alkene increases. Similarly, stability of carbocation, as the hyperconjugation increases, the stability of carbocation also increases. Okay? Okay? Now answer this question. Hyperconjugation is a permanent effect. Hyperconjugation in ethyl cation involves overlapping of CsP2H1s bond with empty 2p orbital of other carbon. Choose the correct option. This is JEE Main 2021 question. JEE Main 2021 question. Who can answer this? Who can answer this question? I'm looking at the chat box. D, both statement 1 and 2 are true. No, bacha, statement 2 is not correct. Because the overlapping is between not CsP2 and HS. The overlapping is between CsP3 carbon and 1s of hydrogen. Always remember, not the CsP2. The overlapping is between the CsP3 carbon and your H carbon. Correct? Correct, because what we were seeing in alkenes. For example, this is the alkene. Can everybody see what I'm writing? This is the alkene, and to the alkene, there's an alpha carbon present. To that carbon, the hydrogens are attached. Correct? So this alpha carbon we are considering, and this alpha carbon is sp3 hybridized. Okay? So the overlapping is between the CsP3 hybridized carbon and the 1s hybridized hydrogens. Correct? So the statement 1 is true. This is a permanent effect, but this statement is a false statement. Everybody got it? Everybody got it? Okay. Next, now we have learnt about these three effects: inductive, resonance and hyperconjugation. Now what happens when I can apply all these effects together? Then you have to consider which effect is given more importance and which is given less. And abhi I told you कि in some molecules plus I effect, like for tertiary cation, the plus I effect is more, but the order reverses for the hyperconjugation. So which one to consider? So the order of importance should be this: resonance, then hyperconjugation, then your inductive effect. Okay, so this should be your order of importance, and how to use it in examples we will do right now. Do not worry, just remember this order, and how you're going to apply it in questions I'm going to tell you. Just remember this thing: resonance is more important than hyperconjugation, then inductive effect. Okay, now let us move to the first question. Now all our entire chemistry is done. You have learnt all the basic things. Now the application part starts, which is the most important part. The increasing order of reactivity of the following compounds towards electrophilic aromatic substitution reaction. Electrophilic, it has about electrophilic means what? It should be electrophilic means what? The more electron rich the ring, more electrophilic reactions will happen. Which means what? The ring should be, the aromatic ring should be electron rich. Then only electrophilic reactions will happen, right? So now tell me the order. Which ring is the most electron rich ring? Yes, Naveen, I'm going to teach you that one by one. We're going to come to all the things. Okay? Right now, we are learning this. B, somebody has said B. Somebody has said B. Very, very good. Very, very good, Krishna. Krishna Veni, Kirti Reddy, you are not right. Shoot out, Jerry. Very, very good. Very, very good. B is the answer. Hemant, you are wrong this time. Game over start, wrong this time. LLL is right. The answer is B. What did I tell you? More electron rich the ring, more electrophilic reactions will happen. So electron rich means what? I have to increase the electron density. So the electron density increases most in this second one, right? The most electron density is second because CH3 is an electron donating group. It will increase the electron density in ring. Then your Cl group. Cl is bacha what? Cl is your, even though it is a minus I effect. Cl shows minus I effect, but it is a deactivating group. Correct? So always remember, whenever Cl is present in your question, it will be somewhere in the middle of the electron donating and the withdrawing group. Okay? It is not completely electron withdrawing group. So the second option is this, and then the third. Third is what? COCH3. COCH3 is this structure, and I told you this here a double bond is happening in the reagent. Double bond means what? It is an electron withdrawing group, right? Double bond always mean an electron withdrawing group. It means it will show minus M effect. I just taught you this will withdraw electrons towards itself, therefore decreasing the electron density. But I want electron rich ring, so therefore this will be the order, which is the B option. Everybody got it? Everybody got it? Okay, next. Next question, JEE Main 2019. The increasing order of reactivity for again electrophilic substitution. Again, right now I taught you. Now nobody will make any mistake in this question. I just taught you. This is a same question, similar question which we just did. Similar question. Electrophilic substitution reaction. Electrophilic substitution reaction. B, B, C, C, B, B, C, C. Very good. Whoever has answered B, you are absolutely correct. Now let me give the explanation of this. Right now I taught you that how the importance of effects will be given. The importance of effects is in this order. Resonance effect is given the most importance, then the hyperconjugation effect, and then your inductive effect. Remember this order. This is the importance order. Resonance, hyperconjugation, and then inductive effect. Now let us look at the Cl molecule, this chlorobenzene molecule. Chlorobenzene actually shows how many effects? Chlorobenzene will show a minus I effect, as well as it will show what? Chlorine has bacha what? It has lone pair. It has lone pair which it can donate, and it can show plus R effect. Does anybody have any doubt in it? Minus I and plus R effect this will show. Correct? Now OMe. What kind of effect OMe will show? OMe has electron rich ring, right? So it will give its electron here, right? It will give its electron, so it will show what? Plus R effect. Anybody has any doubt in it? Okay. Now Me. Me only shows what effect? Me only shows plus I effect. Correct? It only can give its electrons inductive effect. And Cn shows what? Cn is a electron withdrawing group. Correct? It withdraws electron. Therefore, Cn shows your minus I as well as your minus R effect. Okay? Now all these effects are shown. Now what is the correct answer to this? I told you that the most importance is actually given to what? Is given to the resonating effect. Correct? So plus R effect is shown in which cases? It is shown in OMe and as well as in Cl. But as I told you, chlorine as a group is a deactivating group, so it will always be a lesser plus R effect. So therefore more plus R is shown in B. So therefore B will be more electron rich ring, and then it will be what, bacha? Then it will be your, okay, in Me there is another effect which is a plus H, hyperconjugation. Can you see in Me this hyperconjugation? You all forgot about it. Hyperconjugation is also shown because Me is what? A CH3 group. Correct? A CH3 group is attached to a double bond. Can you see a double bond is here? So it will give plus H effect. So the next will be C. Okay? Now next will be what? Next will be your A, and then it will be your D. Does anyone have any doubt in this? Does anyone have any doubt in this? Option B. Yes, option B is the correct. But everybody understood. First of all, because for electrophilic reactions, I need to see which, through which will, I have to see that ring which has the most electron density in it. Okay? So in these options, OMe actually shows the most plus R effect. Correct? So this, because I told you resonance effect is the most important and dominating effect. Next will be what? Next is your Me. Me does what? Me shows inductive effect as well as hyperconjugation effect. Plus Psi and plus H. Therefore, then C option. Okay? And then look at the A option. A has what? It shows a plus R, resonating effect, but it also takes away electrons. है ना? Minus I takes away electrons. So therefore, it comes here, and the D, Cn is only taking away electrons. It is only decreasing the electron density, but I wanted to increase. So Cn will be the last option. Everybody got it? Everybody got it? Every concept should be very, very clear to you guys. Resonance, then inductive, then hyperconjugation, all these things in one example. An extremely great question. Extremely great question. Next, carbocation. Carbocation, you should know a few things about carbocation. Not that it is important, but I am sure you have, you know already so much about it, that more important things that you have to learn is that it has a unhybridized p orbital which is empty. Empty unhybridized p orbital. Its hybridization is sp2. Its shape is planar because it is sp2, so its shape is trigonal, planar, and it has 6 electrons in the valence shell. Okay, only these many things you need to know about a carbocation. Easy. sp2 hybridized, therefore planar structure. It has a vacant p orbital and it has 6 electrons in its valence shell. Okay. Now the stability of carbocation depends on so many factors. Number first, the highest factor is hyperconjugation. I just told you hyperconjugation means what? More the number of alpha hydrogen. For example, if the positive charge is here, right? So the more number of alpha hydrogens are present, more will be the stability of carbocation. This and this. Okay, so more will be the stability of carbocation. Inductive effect means what? More electron donating groups are present. More the number of electron donating groups are present, more will be the stability of carbocation. So it depends on two effects, hyperconjugation and inductive. So more alkyl groups are attached to the carbocation, more CH3 groups, for example, to your carbocation, more the number of alkyl groups are attached, more will be its stability. This is the inductive effect. Hyperconjugation means what? More the number of alpha hydrogens, more will be the hyperconjugating effect and higher will be the stability of your carbocation. Next is resonance. Resonance is also shows resonance. For example, if it is attached with OCH2 group and there's a positive charge, it will show a resonance, and therefore this is a stable structure. Okay. Next, for example, benzyl carbocation. In benzyl carbocation also, what I can do, you can make it's a resonating structures, correct? Just like this, you can move these electrons and this positive charge will move here, right? So you can draw its resonating structure. So this is a stable carbocation. Similarly, alkyl, this is allyl. Okay, allyl carbocation. Allyl means what? Double bond, sigma bond, and a positive charge. This kind of carbocation is called allyl. Okay, this position is called allylic position. This position is called allylic position, which is like a double bond, a sigma bond, and then the carbon. That carbon is called allylic carbon, and if it has a positive charge, it is a stable carbocation. Correct? This is highly stable. But your vinyl carbocation, vinyl means what? When the positive charge is directly on the carbon which has a double bond. So this carbocation is very unstable. This is called vinyl. Very important name. Vinyl carbocation is unstable. Okay. And similarly, phenyl carbocation, where the positive charge is on the benzene ring. This is very unstable. So these two are very unstable, but these two are very stable carbocations. Okay. Next, stability of order of stability of carbocations is this. This is your phenyl carbocation, right? This is your methyl carbocation. This is your RCH2 carbocation. This is R2 CH2 carbocation. This is your R3 C carbocation. Resonance stabilized CH2C double bond plus carbocation. So this is the stability order. Okay. Next, order of stability of some common. So these two are together, bacha. These are the least stable, and then the stability increases. Resonance stabilized are the most stable carbocations. Remember this. Resonance stabilized are the most stable carbocations. What is not visible? What is not visible? I know positive charge is not visible, so I am writing the positive charge here. Okay. Now, order of stability of some carbocation. So this is a benzylic carbocation. This is a benzylic. This is the most stable carbocation. And then comes your allylic carbocation. This carbocation, bacha, is called allylic. This is most stable is benzylic, then allylic, then tertiary carbocation, right? Then your secondary carbocation, then your primary carbocation, and then your methyl carbocation, and then your phenyl carbocation is least stable, or even your vinyl carbocation is least stable. So this is the stability order. Everybody understood the stability order? Does anyone have any doubt in this? Okay. Now next is stability of carbocation. Let us look at the stability order. Aromatic carbocations are more stable than non-aromatic. Important point. Aromatic carbocations more stable than non-aromatic. For example, this is the stability order followed. This is a what? This is a tertiary carbocation, which is more stable, correct? Tertiary is most stable. Then this is a secondary carbocation, lesser stable. Then this is a primary carbocation, least stable carbocation. So this is the stability order of carbocations. Now look at these carbocations. Okay. Now what will be the stability order of these carbocations? Now can you see? Here the positive charge is on CH2 here, CH2 here, CH2 here. That's it. Now what is changing here? The position of the nitro group. Now what does the nitro group does? Nitro group is a electron withdrawing group. Correct? Now this ring is already positive charge. This already has a positive charge and you are withdrawing electrons even more. So this will automatically make the ring unstable, right? So but still you have to tell me which one is more stable between these two compounds, correct? So now what is happening? Here in NO2, this here, okay, now I'll teach you one more very amazing thing. Amazing thing is that the resonance effect is always only shown at the ortho and the para position. Resonance is always only shown at the ortho and the para position. Remember that. And your inductive effect is shown everywhere. Inductive effect is shown in ortho, para, and meta. But your resonance is only shown in ortho and para position. Okay? This NO2 group shows both effect, which is your minus I, electron withdrawing, and minus R, which is your mesomeric, again electron withdrawing effect. So it shows two types of electron withdrawing effects. At the meta position, it only shows minus I effect, because I told you resonance effect is only shown at the ortho and para position. So therefore this only shows minus I effect. Now look at this question. Now this, it is again at the para position, so it will again show minus I and minus R effect, correct? So now you can see that in each case the nitro group is actually taking away the electrons, that I know. But where is it able to take away least amount of electrons? That will be more stable, right? Because it already has a positive charge. So because this NO2 only shows one minus I effect, doesn't show minus I. It is not withdrawing through two groups. Minus I also, minus I R also. No, it is only withdrawing electrons through just minus I. So this one will be the most stable carbocation. Next comes your this. Now here in third and second, both are showing minus I and minus R effect. This is also showing. This is also showing. But we know what? That as the distance increases, the inductive effect decreases. Always remember, as the distance is increasing, my inductive effect, either plus I or minus I, doesn't matter. The inductive effect actually decreases. Always remember this thing. Okay. Now what is happening, bacha? Here, because this group is too far away from the positive charge, therefore the minus I effect here is less. The minus I effect here is less, therefore this carbocation will be more stable and this will be the least stable carbocation, which is first. Everybody understood this concept or not? So from here, what did you learn? This question you learned that the resonance effect is only shown at the ortho and the para position, while inductive effect is shown at all the positions. Second thing, inductive effect decreases with distance. As the distance increases, the inductive effect actually decreases. Everybody got this point? Everybody got this point? Oh. Okay. Next. Now the stability order of again carbocation, which we have given OCH3. OCH3 group is attached at ortho, meta and para position. Now look at this OCH3 group. What this group can do at the ortho and the para position, as I told you. Let's discuss the ortho and para first. At ortho, because this oxygen has lone pair of electrons, correct? So these electrons can participate in resonance. It participates and it will give its electrons. It is increasing the electron density. So therefore it shows plus R effect, correct? But oxygen is what? But oxygen is a very much electronegative compound. So it will always tend to pull electrons towards itself. So therefore at the ortho position it also shows a minus I effect. So here it is showing plus R, which is increasing the electron density. And because this is a carbocation, I need the electrons to be more. Correct? Correct, right? Sorry, my mic fell down. 1 second. Okay. So I need the electron density to increase. So So it is increasing only through plus R effect, and through minus I it is decreasing. Correct? Now in the para position, again there is a plus R effect and a minus I effect. But at the meta position, there is just and just minus I effect. Correct? Now to increase the stability of carbocation, which already has a positive charge. So to increase its stability, what do I have to do? I have to give its electrons, right? So more the electron donating group or more the plus I group, right? More the plus I effect or more the plus R effect, it will actually increase the stability of carbocation. Correct? Because I am already positively charged. So I am positive, I need negative charge to become stable. है ना? So these two effects will increase the stability, but minus I effect will decrease the stability. Correct? So plus R effect is shown in these two groups. Plus R effect is shown in first and plus R effect is shown in third group. But we know in third group minus I is also shown, which is what? Taking away the electrons. But because this para is like very far away, so inductive effect actually becomes less and less as the distance increases. Correct? So this what happens here. Here as the distance increased, the minus I effect decreased. Minus I effect decreased. Right? So this will be the most stable carbocation, then the first, then the third. Does anyone have any doubt in this? Does anyone have any doubt in this? Okay. Next. Let's move on to the next question. Now this is again JEE Main 2023 question. We have done so many examples. Answer me. What will be the answer to this question, bacha? This is a very interesting question. Every question I've attached here, you will learn something new in it. Something new with every question. What decreasing order of hydride affinity for the following carbocation is? Decreasing order of hydride affinity. Answer this question for me. Very, very interesting question. Very, very interesting question. Hydride affinity means what? Which has the highest attraction to the hydrogen atom. Correct? Now let us see the options. In all the options there is a carbocation mentioned. Carbocation, 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 carbocation. Okay. So I know that I have to look at the stability of carbocation now because all are carbocations. Okay. Now after that, what do I have to figure out? I have to figure out the affinity for hydride, which means which will take up an hydrogen atom most easily. So the more stable the carbocation. See, if I am a stable carbocation, will I want to accept any hydrogen? Will I want to accept any? No, I am already stable. Why will I accept any hydrogen atom? I will not accept any hydrogen atom. Correct? So in this same thing happen, bacha. The more stable the carbocation, it will not accept hydrogen, so hydride affinity becomes lesser. Okay. So can you see the least stable carbocation here? I can see is perfectly this one, which is a secondary carbocation. Okay. This A option is a tertiary carbocation. I'm really sorry. That is not secondary, that is a tertiary. One second. Yes. Okay, everybody got this point? Right? So here what will happen? How will you check the stability of carbocations, bacha? How will you test the stability? In A, I can see that there is some kind of resonance happening, correct? This bond can move here and this positive charge can move here. So here it is showing bacha resonance effect, correct? And in this question, these are all benzyl rings attached. So this is a benzylic carbocation, which is also a tribenzylic. C6H5 is what? Benzyl. So this is bhaiya ji बहुत stable compound. This is more stable. And this is a tertiary carbocation, This is a benzylic carbocation. Okay, and this carbocation, bacha, which is given in your question in 2023, is the best example of the most stable carbocation. This tricyclopropane carbocation is the most stable carbocation. There is no carbocation in the entire world which is more stable than this one. Always remember, I will let you know the stability order of every carbocation known in the universe. Okay, most stable carbocation is this one, which is mentioned, which is a tricyclopropyl carbocation, is the most stable in the world. Next come is this carbocation, right? This carbocation, how many carbons are there? 1, 2, 3, 4, 5, 6, 7. 7 carbocation, which means what? Cyclohept trienyl carbocation is the next most stable carbocation. Okay, next comes what? Next is the carbocation this, to which 3 benzyl rings are attached. This carbocation is then the next stable carbocation, benzyl ring, correct? And here after that it is this carbocation, tertiary, CH3 and CH3 carbocation, correct? And then the tertiary carbocation is the most stable, and then whatever order is given you can find out. But this is like the most stable carbocations ever known. So whenever stability order is asked, this order you have to follow. Till now in your JEE exam, this carbocation is asked, this carbocation is asked, and this carbocation is asked, but till now this carbocation still remains to be asked. So I have a very gut feeling that this year about this carbocation your examiner will ask, because he has not asked this yet. So you have to know each and everything, how the brain of your examiner functions. So this carbocation is the next most stable carbocation. Okay? So now we have learned about the stability of carbocations, right? So I told you the more stable carbocation is, more the stable carbocation, it will not accept any hydrogen. I'm already stable. I don't need any hydrogen. So it will have the least hydride affinity, right? Now let's go back to the question again. This is your question, right? So now I know that D is the most stable. I'm writing down the stability of carbocation first. So D is the most stable. Then comes your B carbocation, which is benzylic. Then comes your C carbocation, and then is your resonance stabilized A carbocation. This is the stability order. Everybody understood? No. DB. Okay, 1 second, bacha. 1 second. Let me make one correction. One 180-BT correction. 180-BT correction is here. Understand this thing. Here, this is also a tertiary. This is a tertiary carbocation again. This is also a tertiary carbocation. But in this, there is resonance also. How can we miss that? We cannot afford. Resonance is present, means more stable, even though both of them are tertiary, but this also has resonance stabilization. Therefore, stability is D, B, A and C. This is the carbocation stability. Therefore, affinity for hydrogen will be the reverse order. More affinity will be of C, then A, then B, then D. So, B option is your correct. B option is your correct. The most C will be more affinity, then A, then B, then D. Everybody understood? Everybody understood this question? Okay? Now let's move on. JEE Main 2022 question. Easiest question ever asked. Answer me this question. Which of the following carbocation is most stable? Easiest question ever asked in your JEE exam. If you do this question wrong, I'm really sorry. They cannot make any easier question than this. Answer this question. Answer this question. I am looking at the chat box. Everybody. I am looking at the chat box. Everybody. D. Very, very good. The first person to answer is Harshnikesh, and then Surya Narayan, and then Sahasra. Very good. Not A, it's D, and Uchuk. Okay, that's a really funny name. Uchuk Puchuk. This is true. The most stable carbocation is D, bachcha. Kyun? Kyunki it is the most resonance stabilized. Can you see this? This can move here, this can move here, and this can move here. So this positive charge will keep moving here and there. Therefore, it is most resonance stabilized carbocation. Next, very amazing question. I love these questions. Sometimes organic makes me fall in love with it. I'm seriously telling you, organic chemistry is so beautiful. I mean, it is like solving a puzzle, solving a riddle. You have so many, you know how mystery novels work? That there are so many clues here and there. You just have to like figure it out and find out who's the murderer. In same here goes on. There are so many clues. Oh, oxygen does this. Oxygen has electron pair. It donates, but it is also very electronegative. So it also accepts electrons. Correct. So it is also electron withdrawing, but also electron donating. So many effects are working. You have so many clues, but then you have to form the right opinion based on all the knowledge. You know, when you mix all your knowledge and then form an opinion based on so many knowledge, sphere of knowledge, that's how you become a wise person. So organic chemistry makes you a wise person. If you are very if you like solving mystery novels, this is the best. Next thing to do in academics is to do organic chemistry. It is super fun, super fun. Now answer the question. Answer the question. A. I have received so many answers. A answer seems to be the most common answer. Very good. A answer is correct. A answer is correct. Okay. Why is B most stable, bachcha? I will explain to you everything. B is most stable because it is resonance stabilized carbocation. The oxygen can give the electron pair here. It can get a negative charge. So this is a resonance stabilized. Most stable is B. Then C is the least stable. Then comes A, because A has bachcha what? A has your hyperconjugating alpha. This is alpha carbon, this is alpha carbon. Hydrogen, 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 hydrogen. Correct? So first is the resonance. I told you whenever there are so many effects, resonance will get the most importance. So resonance is present here. So therefore this is the most stable carbocation. Here hyperconjugating structures are present due to these hydrogens, 4 hydrogens. So then comes A stable and then comes your C stable. ठीक है? C. Answer me this question. The correct order of stability of given carbocation. This is the easiest question. Again, easiest question. Everything. If you know everything, each and everything I taught you today, then you must be able to answer this question. I will give you a little hint. Carbocation. For example, if I am a negative charge, I told you a negative charge is most stable. Where? A negative charge is most stable on a more electronegative atom, right? For example, a negative charge is stable most on oxygen, then on most on fluorine, then on oxygen, then on nitrogen, right? So this is how a negative charge is most stable on more electronegative elements. Similarly, a positive charge will be more stable on a lesser electronegative element, correct? On a lesser electronegative element. This is the approach. Now answer this question. Now answer this question, everybody. Everybody. Hello guys, A answer is coming. Let us see what is the answer is actually A. Correct answer. Now let me explain why. Let me explain why. See, A is the most stable carbocation. Why? Because this is a benzylic carbocation. I told you benzylic carbocations are very stable because it has so much of resonance. Correct? A is the most stable, which is true. Now look at the positive charge. Look at the positive charge here. It is on the double bonded carbon, here it is on the single bonded carbon, here it is on the triple bonded carbon, right? So here on the double bonded carbon, can you see? Here on the double bonded carbon, it is sp, what hybridized? This is sp2 hybridized. This is sp3 hybridized carbon, and this is sp hybridized carbon. This is clear to everybody, right? And we know that sp hybridized carbon is the most electronegative carbon, correct? So if this carbon which is sp hybridized is most electronegative, why it will take a positive charge? It will not. It is the most unstable because it is so, imagine it in this way. Most electronegative comes to your what? Mind. What atom comes to your mind? It is oxygen, right? For oxygen atom, what happens? Oxygen is electronegative. Imagine if on oxygen I put a positive charge. So on oxygen, that positive charge is not stable at all, correct? Similarly, because this carbon is most electronegative, imagine it like just like oxygen, just like how you put a positive charge on oxygen, it's not stable. Similarly, a positive charge on a highly electronegative carbon is not stable. So therefore, sp3 carbon, which is your C, is more stable than your sp2 and then your sp carbocation. Everybody understood this? Everybody understood? Correct. Now let's do ring expansion, and this will be the last topic for today's class, ring expansion. Why? I know there are so many things remaining right now, but what I have done in today's session, bacha, is we have covered all the basic things which nobody teaches you, but every year comes an exam. We have seen every year these things comes an exam, but the rest of the things after ring expansion, you know what will be remaining? The only thing that will be remaining will be your name reaction and also the ortho effect of your carboxylic acid. I will give you a basic idea of ortho effect of carboxylic acid. That's it. And after all the other things which you want in form of summaries, everything is included in the slides, which I will provide you in the PDF, all the name reactions with all the reagents. For example, what does lithium aluminum hydride reduces? It reduces aldehydes, ketones, but it doesn't reduce acids, and all those things which are facts. I cannot teach you. Nothing happens lithium. You just have to learn ki, okay, it reduces this. So you can look at the PDF and know for yourself. In the PDF, it is given in the most easy format, okay? So you can just go and read it. I know within 4 hours we cannot complete the entire thing, but whatever we have completed, it's the best chemistry lesson you can get before your chemistry exam. That is my guarantee, my promise. Okay, now come to ring expansion. Very easy topic, ring expansion topic. In ring expansion, for example, whenever there is a H plus attack on this OH, these kind of reactions are asked every year, and what will happen in this ring expansion will happen. And two kinds of shift you will learn, 1 to hydride shift, 1 to methyl shift. Please make these concepts clear in this class. I will make it clear and you will never have any doubt ever again. So what is happening? This is a H plus sign. We know this is positive charge. So oxygen has what? Lone pair. So these lone pair actually attack your H plus. So when it attacks your H plus, this H plus will get attached to this here. Now let us look all the steps that happen. Here what happened? This H plus got attached here and this became OH2 plus. OH2 plus, it is very unstable, good leaving group, it leaves and there is a carbocation formed here. And we know that a cyclobutane and this is a cyclopentane. These rings are unstable. The most stable ring is actually a 6-membered ring. So any ring which is not 6-membered will want to be a 6-membered ring, correct? So now what will happen? This positive charge, the cyclobutane ring, here it will break, this bond will break and it will expand itself and become a cyclopentane ring. Okay, so this will break and this will get attached here and a positive charge comes here. Now notice one thing, the bond which I am breaking, okay, and this bond I am breaking and I am attaching here, and this positive charge actually attacks the other side of the carbon. Remember this, I am breaking this bond, the positive charge goes there. Okay? Now this positive charge is what? This positive charge is a secondary carbocation, right? This is a secondary carbocation. Now it can do what? It can become a tertiary. So what will happen here? A 1,2 hydride shift will happen. A hydrogen from this place will actually go here, correct? And the positive charge comes here because tertiary carbocation is more stable. It becomes a tertiary carbocation. Now again what happens? This bond now attacks this positive charge because it is still a 5-membered ring. It can still expand. So this bond breaks and this attacks this positive charge. So the positive charge now travels here and attaches here, right? Now this 5-membered ring became a 6-membered ring and the positive charge came here. This kind of compound which is attached, which is 2 rings attached with 1 carbon center. Can you see? This kind of compound is called a spiro compound. What is it called? It is called a spiro compound, right? Now this positive charge which is here, bacha, correct? This positive charge, again this is the 6-membered ring but this is a 5. So this ring will again break and it will become a 6-membered ring again. Okay? And here it will be the positive charge. Now let us go back to the question. Here it is given, heat is also given. So after this positive charge, when you are heating it, so when you are heating it, what happens? It takes away the H plus ion again and the alkene develops here. Only and only, you have to make an alkene only and only when heat is given in the reaction after reacting it with H plus. Okay, so with H plus what we have done, we have expanded the ring, done ring expansion. You must understand each and every step because same question will not be repeated but similar kind will obviously come. There is no second doubts about it. Well, surely, because every year it comes. Obviously this year will also come. This is a basic chemistry question you need to know. And from spiro ring it gets converted into, now this ring is attached to 2 carbon centers. This is called a bicyclo compound. Okay, you must know the names of each of these compounds. And when we heat it, a hydrogen gets removed from here and the more substituted stable ring, this is the most substituted alkene forms. Okay, so this is how you approach these reactions. Very important reactions, correct? Now next question is again similar question. Right now we did a hydride shift, 1,2 hydride shift. That was again a 2023 question. This is again a 2023 question in which again see there is a OH atom here and you are again attacking what? H3O plus, which means what? Again a H plus ion. Same attack. This H plus attacks here, this become OH2 plus, this gets removed, here comes the positive charge, correct? Now let us look at the reaction mechanism. I have done this becomes H2O plus, this gets removed and the positive charge come here. This carbocation is what? This is a secondary carbocation, right? But if this moves here, it can become a tertiary carbocation. But already can you see on this carbon 3 methyl groups are already attached, correct? So here what will happen? 1,2 methyl shift happens and the entire methyl shift over here so that this becomes a tertiary carbocation, correct? Now count the number of carbons it has. It has 1 carbon, 1, 2, 3, 4, 5. 5 and this is the 6th carbon. So it can actually form a 6-membered ring, correct? So this positive charge attacks this double bond. Double bond is what? Electron rich. So this electron rich double bond attacks this positive charge and forms a 6-membered ring compound with the positive charge coming here, right? Now can you see in this reaction there is no heat given, so alkene will not be formed. Instead what will happen, we will again take out the H plus from here and it will form a majorly substituted alkene here, correct? Sorry, alkene will be formed in both the cases. Next question is carbanion. And for the carbanion, the things that you should know. The things that you should know in carbanion is its hybridization is sp3. Its geometry is trigonal pyramidal and it has a lone pair of electron in its valence shell. In its valence shell, how many electrons are there? 8, and its p orbital 8 electrons are present, correct? And the stability of carbanion, so we have already done the stability of carbocation, right? So as I am increasing the methyl groups or the electron donating groups to a carbocation. So the stability increases. So the stability of carbanion is the opposite of carbocation, right? So as see here the carbanion again, the carbanion, this one, benzylic carbanion is the most stable. Obviously because it has the most resonating structures, it is the most stable carbanion. Okay? Next is the allylic carbanion. This is the allylic carbanion. Okay? This is again, one second. Let me change the pen color. Here. This is the benzylic carbanion. This is the allylic carbanion. Right? Now these two are very, very stable. I understand. These two stability is same as the carbocation stability order. But after that, most stable carbocation is the methyl. Then it is your secondary carbocation. Then it is your tertiary carbocation. And then is your primary, secondary, and then tertiary carbocation. Correct? So this is the order. Methyl is more stable. Methyl carbanion is more stable than primary, is more stable than secondary, is more stable than tertiary carbocation. Everybody understood this concept? Everybody understood? Beta, we have done the stability orders. We have already done. You are late to the class. We have done the stability orders. Beta, we have done the stability orders, okay? Now, stability of carbanion. Can you see here? Here, first is your allylic. This is your what? This is your allylic carbanion. So, this is the most stable. Allylic, right? And this one is vinylic carbanion. And this one is your CH3. Why is this following this pattern, bacha? Because this is a negative charge on a sp2 hybridized carbon, and there is a negative charge on a sp3 hybridized carbon, right? Because sp2 is more electronegative, therefore the negative charge is more stable on second, and then it is the least stable on sp3, but still it is more stable in first case because it is a allylic carbanion. Allylic things are always stable, whether carbocations or carbanions or free radicals, whatever. Allylic and benzylic things are always most stable things. Okay? Okay? Next stability order. Stability order of carbanion. Can you see? Can you see? Now these things I can give you as homework or not. We have already discussed the stability of carbocations using these things. Do you remember? NO2. NO2 group is a electron withdrawing groups. At the ortho and para position, it shows what all nature? It shows a minus I as well as minus R nature. Here it shows just minus I nature, and here it shows minus I as well as minus R nature. Correct? And in the carbanion, it is already a negatively charged species. It means if I am removing the electron, it is becoming more stable. Right? So I think the first, this ortho position, minus I and minus R both are there. This is the most stable. First is most stable, right? Second is only showing minus I. So this is the least stable. And third, it is showing both minus I and minus R. But minus I is less in this because the distance has increased. This is the para position. As the distance increases, inductive effect decreases. Therefore, this has the least amount of third has the lesser amount of stability. The same order will be followed in this case. I will write down OCH3 at the ortho position gives what? It gives plus I effect as well as it gives plus R effect. Correct? Nee, minus I effect. Sorry. It gives minus I, not plus I. Correct it. Yes. It gives minus I and plus R effect. On the meta position, it just gives minus I effect. Here it gives minus I and plus R effect. So based on this effect, the stability order is second because it is just showing minus I. It is the most stable. Then your first, then your third. Everybody is understanding what I'm trying to say right now. Okay, kids, thank you so much. Thank you so much. If you're understanding, that is a very good sign. That is a very good sign. Thank you so much, students. Now let us do this question. Which will undergo deprotonation most easily in the basic medium? In the basic medium, which will undergo deprotonation most easily? Who will answer this question? Deprotonation. Deprotonation means what? Removal of a H plus ion. Removal of a H plus ion. Correct? This is deprotonation. Removal of H plus ion. If H plus ion is removed, which means what? A carbon ion will be formed here. A carbon ion will be formed here. A carbon ion will be formed here. Correct? Correct? And why have I taken out hydrogen from these positions, ma'am? Why not anywhere else? क्योंकि बच्चा यहाँ पे what is put? This oxygen is what? Electron withdrawing group, right? So therefore this makes these hydrogens the most acidic hydrogens. If electron withdrawing groups are present, the hydrogen next to it is the most acidic hydrogen. It means it will get removed easily. Correct? Here also 2 electron withdrawing groups. Here also 2 electron withdrawing groups. So here when I do deprotonation, if I am removing H plus, so what will remain here? A negative charge, a carbon anion. Now tell me the stability of carbon anion. So which will undergo most easily deprotonation? Which will form the most stable carbon ion? Easy concept. Easy concept. Which will form the most stable carbon anion? What will be the answer? A. A answer. Hish, Nikesh, Uchuk, Puchuk. Everybody, Harsh, Nikesh, sorry. Harsh, Nikesh, okay. A only, very, very good. The answer is A. And why is that? Why is the answer A of this question, bacha? Kyuki, can you look at this formula? Okay. Now here what is happening? Only electron withdrawing groups are here. And it is already negative charge. So if I am putting electron withdrawing groups, I am increasing the stability. Obviously, right? If I am negative, I don't want to be negative. So yes, attach withdrawing groups to me. I am more stable. Here what is happening? The oxygen group here is present, which has a lone pair of electrons. And what this lone pair of electrons will do? This lone pair of electrons will, okay, this negative charge can also go in resonance. This negative charge can go here and it can go here. It can go here and it can go here, right? This negative charge can undergo resonating structures, right? But in this, what will happen? In this electron pairs will also undergo resonance. Okay, and this will also undergo resonance, this will also undergo resonance, and this will also undergo resonance, right? So what is happening ultimately? That this negative charge is not getting chance to resonate more because it is these electrons are already occupied by the MEO group. So this will not be stable. Similarly, here also 1OMe is present. Again these electrons will be occupied for resonance. So therefore this has a lesser chance of resonating. Therefore this carbon ion is not that stable, but this one is most stable. Are you guys understanding everything? Sound glitch? Is it better now? Can anybody answer to me? Is it better? Deprotonation. Proton means what? Proton is H plus. Proton means H plus. Deprotonation means removal of proton. Okay. So it means I am removing H plus minus H plus. Okay. I am removing H plus from this. It means deprotonation. Okay. Kriti, I have told you what is deprotonation. Can you hear me now? Can you hear me now? Hello. Can you hear me, everybody? Beta, I've told you, Kriti, what is deprotonation. ठीक है. Now tell me which one has the most acidic hydrogen. Which one has the most acidic hydrogen? JEE Main 2020 question. Most acidic hydrogen means what? Which will give H plus easily. Correct? It will be the most acidic hydrogen, which means what? Which will have the most stable carbanion. Correct? Whichever will have the most stable carbanion will be the most acidic hydrogen. Now tell me, which one will be the most acidic hydrogen? A, B, C, D. A, B, C, D. A, B, C, D. Tell me, I'm looking at the chat box. Nobody's answering. Nobody's answering. Okay, tell me one thing. This is a sp hybridized carbon. I know. This is a sp hybridized carbon. Okay. This is a ketone group. So this will again this group will again, what it will do? It will attract electrons towards itself, right? Electron withdrawing group. This is also electron withdrawing group, and these are also electron withdrawing groups. Correct? But can you see here again OMe is present everywhere? Can you see OMe is present in the D option? So this OMe will actually take part in resonance, right? So this proton which is present here will okay, let me explain it in a better way. I'm just a little bit tired. I'm really sorry about that. Yes. So what is happening in D option? Even though there are 3 electron withdrawing groups are attached to it. So when I take out this hydrogen, what will be remaining here? A negative charge. A carbanion will be remaining here. Correct? So this carbanion, even though there are so many electron withdrawing groups attached to it to make it stable, but can you see OMe group is also present here, which will take part in resonance, right? So therefore this anion which has formed will not get a chance to take part in resonance. So this will not be the most stable carbon ion. Now let us look at this. This can be a stable carbon ion, but can you see the C option? C option has 2 very strong electron withdrawing groups attached to it. Cn is a very strong electron withdrawing group, and if I take out this hydrogen and a negative charge comes here, this negative charge will be balanced by this Cn and by these electron withdrawing groups. So this will be the most stable carbanion formed. Hence, this hydrogen will be the most acidic hydrogen. Does everybody understand this? Everybody understand this? Huh? Yeah, I didn't ended it or huh? No, I'm not. It's showing the live ended. Or I'm back. Okay, sorry. Bye. Hello students, I thought the live ended in the middle, right? What happened? Sorry students. Where is the live? Yes. We are back. I'm really sorry for the lag. Did the live end? Even the live ended for me as well. Oh my god, what happened? Hi. Okay, students. I think so did you understand? I don't know where till where did you hear? I just told you because these are two very strong electron withdrawing groups. So because this is a negative charge, the electron withdrawing groups will balance out the negative charge, and hence this hydrogen will be the most acidic hydrogen because the carbanion formed here is the most stable carbanion. Okay. Something happened to the live. I don't know what happened though. Correct. And then free radical structure you should all know. The free radical is a neutral radical. It has 7 electrons in the valence shell. It is highly reactive. Very important thing. It is short-lived and its hybridization is in between sp2 and sp3. These are many important points for the free radical. Okay? Okay? Beta, you can always go back and see the entire video once the video ends. Correct? You can always go back. This video is saved. Don't worry. For example, if the free radical is CH3, then the hybridization is sp2. But if a more electronegative element is added, for example CF3, the hybridization becomes sp3. So in sp2, okay, so this is the hybridization model here. And if I am comparing the alkyl free radicals experimentally observed, then just pay attention that as the alkyl groups are added, as alkyl groups are added to the free radical, the hybridization becomes more and more sp3. Here the hybridization is more and more sp2. Okay, understand the hybridization concept. Now let's move on to the stability of free radical. Stability of free radical. Okay. Bacha, once the live, I know probably it can be showing 3 minutes right now, but once this session ends, I'm going to end this session right now before 5. Then you can go back and see the entire 4-hour session whichever we had. Okay, it's almost a 4-hour session. Next, more resonance, more stability of free radical. Correct. More the same stability order will be followed. As the resonance increases, for example, this bond can move here and the free radical can move here, right? As resonance increases, for example, the resonance is most in the third because there is a double bond here and a double bond sigma bond here. So this has the most resonance, then this, and then this one has the vinylic free radical has no resonance. So the stability order is actually third is more stable than first, then second. Correct. Now the stability order of the this carbocation, free radical. Free radical. Now look at the resonating structures. Now this resonating structures, it can actually delocalize. Correct. This has the most resonance. Then this has only one double bond, so this has a lesser resonance. And in this is a benzylic free radical. Benzylic free radical, bacha, is not stable at all because it is a localized. It means this free radical does not move inside the benzyl ring. So this is not stable radical. Correct? The benzylic is not correct. So we have studied everything. Now the next thing that is left is aromaticity. I am pretty sure that everybody is super aware with what aromatic compounds are. Aromatic compounds are actually cyclic, planar, conjugated. These are the basic conditions for any aromatic compound. Cyclic, planar and conjugated. Correct. So if these three conditions are satisfied, then we come to know whether the compound is an aromatic compound or an anti-aromatic compound. Correct. And if only these three conditions are not satisfied, for example, the compound is not cyclic, not planar, or not conjugated. Conjugated means what? It has double bonds in conjugation, SA. Correct. And cyclic means what? It is always in the form of a cycle and it has conjugated double bonds. Correct. And every atom should be sp2 hybridized or sp hybridized. Planar means what? Planar means sp2 or sp hybridized carbon should be there for it to show what? Aromaticity. If any of these are not met, then those are called non-aromatic compound. And if all these three conditions are met, right, if all these conditions are met, and if the number of electrons, if it follows Huckel rule, which is 4n plus 2 pi electrons are present, then that compound is an aromatic compound. These are the examples. And if 4n pi electron rule is followed, then the compound is an anti-aromatic compound. Does anyone have any doubt in this? Okay? Yes, correct. Now we're going to look at some very good exceptions. These are extremely great examples. Look at these exceptions for aromaticity. Now this kind of compound, bacha, it is called a aniline compound. What it is called? It is called aniline. Correct? In this aniline, what can you see? Is this a cyclic compound? Yes, this is a cyclic compound. Is this a conjugated compound? Are the double bonds in conjugation? Yes. Are all the carbons sp2 hybridized? Yes. So it is following all the conditions. And now count the number of double bonds. It has 1, 2, 3, 4, 5. 5 double bonds means what? How many electrons are there? There are 10 pi electrons, which means it is following the Huckel rule, which is what? 4n plus 2 pi electrons. Correct? So it must therefore be aromatic, ma'am. But it is not, because bacha, this compound is not planar. Why? Because these two hydrogens which are present on this bridge heads, right? These two bridgehead hydrogens are actually cause steric hindrance to each other, and therefore this ring, which has to be planar, is not planar. It actually twisted. So the plane of the ring is twisted and it is not planar anymore due to these hydrogens repulsion. Therefore this compound is a very good exception, and this is a not aromatic compound. This is a non-aromatic compound. Okay, because this is not planar. So this is a non-aromatic compound. Very good example. Very good. Okay. Next is cyclooctatetraene. Again a very good example. Count the number of double bonds. This is a cyclic compound, right? This is all carbons are sp2 hybridized. All double bonds are conjugated. How many double bonds are there? How many electrons are there? 1, 2, 3, 4. It means it has 8 pi electrons, which means it should be anti-aromatic compound. But cyclooctatetraene is again a non-aromatic compound because this compound is not planar. This compound is actually in a chair form, like this. Therefore this is not a planar compound. Therefore this compound is actually a non-aromatic compound. Always remember, these two are very good exceptions. That one was also a aniline. Due to the hydrogen repulsion, the plane of the ring twists and it becomes a non-planar compound. Everybody understood? Next. Now let's do the last question of the day, and till now we have done almost everything of organic chemistry. This is the last question of the day. Which of the following structures are aromatic in nature? What is the answer to this question? Which of the following structures are aromatic? What is the answer to this question? What is the answer to this question? Nobody is answering. Bacha, tell me what is the answer to this question. only A and C are aromatic. Only A and C are aromatic. C. Alvin has given D answer. Advai Senthil Kumar has given C answer. Let us look at the Sahi answer is, nobody gave the right answer. The right answer only given by Sanjay. Only Sanjay has given the right answer, which is only A and B. Very, very good. Now let us look which are aromatic in nature. Are here the compound is cyclic? Yes. A compound. We're talking about the A compound. The compound is cyclic? Yes. How many and are all the are all these things sp2 hybridized? Yes. Okay. And how many is this planar compound? Yes. And next thing which we have to see, how many electrons are there? Here it is 2 electrons, 2 electrons and 2 electrons. It means this has 6 pi electrons. How many electrons this ring have? This ring again have 1, 2, 3, 6 pi electrons. So both of them, bacha, have 6 pi electrons, are cyclic, planar, right? So these are aromatic. Now count the number of electrons here. 1, 2, 3, 4. So it has 8 pi electrons. Therefore, this is anti-aromatic. Correct? Now count the number of electrons here. This has 1, 2, 3, 4. This negative charge is also there. So again it has 8 pi electrons. 8 pi means what? 8 pi means anti-aromatic. So to determine what is anti-aromatic, bacha, if it comes in the table of 4, it is anti-aromatic. 4, 8, 4 2s are 8, 4 3s are 12, 4 4s are 16. If it comes in the table of 8, it is what? It is a anti-aromatic compound. Correct? So this answer was given correct only just by Sanjay. So bacha, I am going to end this session here. We have discussed almost every effect, every basic nook and crook thing which will help you in your JEE exam. This is the session to attend. Correct? If you have friends who are weak in organic chemistry and need a one-day boost to give them at least acidity, basicity order, how to approach the reactions, how to know which is the carbocation, which is the carbonyl, which will be stable, which will be not stable, all of those things. And if you are the kind of person who want to revise everything from basic to the end, including the name reactions, then I will provide the PDF on the Telegram link tonight. So please go and subscribe to the Telegram channel at this moment, which is very, very essential to you guys. And thank you so much for attending this class. I will see you again sometime later. I will see you again in your JEE exams, correct? And we will discuss the questions and answers together from 27th onwards. Goodbye and have a great day, everyone. Abhi, there is another marathon going on. You can go and attend that on the same channel. Thank you so much, guys. Bye-bye. Bye-bye. Thank you. Thank you, everybody. Thank you, Alvin. Thank you. Bye-bye. And please comment down below session kaisa laga, so that I also get the feedback. Okay, always please comment down whatever is your feedback, negative, positive, neutral, whatever. Let us know. Let's develop a parasocial relationship where you and I get to interact and know each other through the comment section of the box. Okay, thank you. Bye bye.